I would like to say, okay. So first, I would like to say I'm honored to be invited to give a talk at CLIC. I'm sorry I cannot attend the on-site conference. I hope we can have some. So can you hear me?
Guru, I apologize. We're not getting audio in the room right now from the talk. Trying to figure out the best way to get this hooked in.
I'm sorry. Can you hear me?
Yes, we can hear you now. That's perfect.
Okay, good. So, so back to my presentation. So today my topic is about image and video compression for machine. Okay. So traditional image and video coding has a long history, and a lot of coding standards such as JPEG and H.264 has been widely used in our daily life. So in recent years, we have also witnessed the success of learned image or video compression. And the current state-of-art image codec already outperforms the latest standards such as H.266. So I don't intend to introduce too many recent works on this field. And I think most people in this workshop are very familiar with this topic. It should be mentioned that most existing work try to achieve better rate distortion trade-off, where the distortion is measured based on the human visual system. So the reason is that we have an assumption that the image are mainly watched by a human. So a lot of metrics for human visual system have been proposed in the past decades, and the existing codec are optimized based on this quality metrics such as PSR, multi-scale SSM, or VMAF. So this direction is very important, and the community has achieved a lot of progress in the past few years. But nowadays, deep learning techniques has significantly improved performance for image or video analysis tasks, such as classification. So more and more video are not purely watched by humans. They are analyzed by the deep learning models. Therefore, we have some new scenario which have different requirements for the image or video compression task. For example, in autonomous driving, the vehicle will capture image or video and send them to other vehicles or edge devices. This visual data will be analyzed based on the deep learning model and are used to make decisions in the driving stage. So it is obvious that this visual data will not be directly watched by human, and they are used for the downstream visual analysis tasks such as video action detection or segmentation. Some reports show that nearly 4 TB data will be generated by one car in 1.5 hours of driving. So it brings a lot of transition and storage burden in practical applications. Another exemplary scenario is the AI city, where a lot of camera will capture video data and send them to the cloud server for analysis. So in fact, this machine-to-machine connection becomes more and more popular and increased to 50% according to Cisco's report. So we cannot ignore that this emerging requirement for the image and the video codec. And in these scenarios, the visual quality is not top priority, and we care more about the performance of the downstream task. Therefore, there's a shift in the objective function from rate distortion balance to rate accuracy balance. So the accuracy may represent the performance of the downstream analysis task. So to solve this problem, several approaches have been proposed in the past few years. So Since the learned image compression is very popular and is differentiable, it is very straightforward to directly optimize the downstream video task with the image codec. And the whole framework can be end-to-end optimized based on the read accuracy trade-off. So experimental results also show that this solution can bring a significant bitrate reduction in the transition stage. Another solution is the scalable coding-based approach. Here, I'll give an example for this method, and it is a scalable coding-based approach for machine vision. It has two branches, the base branch and the enhancement branch. And in this paper, the author focused on the face recognition. So in the base branch, it employs the face net to extract raw feature, which are useful for the downstream analysis task. Then these features will be compressed by using the existing image compression network, and the decoded feature or the reconstructed feature will be used for the analysis task. And this design can provide better rate accuracy trade-off. And it should be highlighted that the author also introduced the feature to texture modular, where the decoded feature will also be used to reconstruct an initial RGB image. Although the initial image or the basic image is not perfect, it provides some useful texture information and reduce the reconstruction, reduce the bitrate cost for the reconstruction of the original image. So in the enhancement branch, the residue between the original image and the basic image will be is further compressed by using another autoencoder based compression network. Finally, we can get a high quality reconstruct image based on the bit stream from the enhancement branch. So the whole framework is end-to-end optimized with one specific machine vision task. So compared with the straightforward solution, it can support both the machine vision task and the hemio vision system based on the scalable coding framework. Although the existing works have provided some interesting solutions and the results, there are also some challenges in the practical applications. First, most of the existing works have to rely on the learned image or video codec to achieve the end-to-end optimization. However, the computational complexity of the existing learned image or video codec is still huge. Although several proposals have been proposed to reduce the computational cost for learned codec, it still needs more efforts before they can be used in the practical applications. For example, the encoding speed of the X265 codec for 2K video will be more than 30 FPS, while the corresponding encoding speed of DVC or other learned video codec is only 1 or 2 FPS, even they use the GPU platform. Another problem is compatibility. Since we already have a lot of image and video coding standards, and the hardware can support this method while we do not have a learned image or video coding standards. So the existing pipeline cannot support the learned codec, which also brings a new challenge for this method. In addition, the generalization ability is another challenge. The previous work optimize image codec for some specific applications. For example, the image classification. For example, the image classification, while we are not sure whether the decoded image or feature can also be used for other applications, such as object detection. Since the decoded image or video may be used for different tasks, it would be better if the whole framework has a strong generalization ability. So to address this challenge, we try to combine the advantage of both neural networks and the traditional codecs. So on the one hand, we use a powerful neural network to extract features, and on the other hand, we can rely on the traditional codec, which are faster and standard compatible. Finally, we hope this combination can be beneficial from the machine vision tasks. We name this pipeline as a hybrid compression for machine. So here, I introduce some recent work from our group as on the compression for machine. The first work is the pre-processing enhanced image compression for machine vision. So in this work, we introduce a neural network-based pre-processing modular for non-differentiable traditional codec like BPG. Compared with the traditional compression pipelines, only difference is the pre-processing modular, and the compression still rely on the traditional video codec, traditional image codec. So the bit stream are compatible, and the decoded image can be directly used for the downstream machine vision tasks, such as image classification or detection. Okay, in this slide, we give more detail about our framework. It's very straightforward for our inference or the forward stage in the training procedure. So given the input image, it will be sent to the pre-processing modular, and the output will be compressed by the traditional codec. Here we use BBD as an example. And then the decoded image will be used for the downstream machine vision tasks, such as image classification. The last function is based on the rate accuracy trade-off. For example, for the image classification, we will use cross-entropy loss, and we will also introduce the rate term in the optimization stage. However, the traditional codec like BPG are not differentiable, and we cannot directly optimize the whole framework in an end-to-end fashion. So we introduce a proxy network in the back propagation stage to approximate the traditional codec. Specifically, we use the existing learned image codec as the proxy network, and we hope the results from the proxy network and that are similar to that from BPG codec. Then we fix the proxy network, and the gradient will be propagated to the neural processing modular through the proxy network. Then we can optimize the pre-processing modular based on the rate accuracy loss, and we hope the output image from pre-processing modular is easier for compression, and the output image are also beneficial for the downstream tasks like classification. So here is a network implementation of our proposed pre-processing modular. It has two branches, and we use the plain network to extract the textual information, while UNet style network is used to generate the structure information. Finally, the results from these two branches are fused to generate the final pre-processing results. Considering we will deploy the proposed processing model at a different bitrate setting, which means the BPD codec has different quantization parameters. So we further integrated a quantization adaptive layer into the pre-processing modular. This adaptive layer will generate a scale vector to modulate the intermediate feature in the pre-processing modular. And the output results will be conditional on the quantization parameter from BPD codec. Therefore, it will enable the proposed method to generate the optimal filtered image at different bit rates. Okay, here we give some analysis of the pre-processing modular to demonstrate the advantage of our pre-processing modular. We provide some visualization results. So image A and B are the original image, and the output results from pre-processing, and the image A and B are the original image, and the output results from the pre-processing modular. So image C is a residue between A and B. It is observed that the information we discussed in the pre-processing modular is mainly distributed in the background region, such as graphs. While according to image D, the image classification network put more attention on the foreground region. So our approach can reduce the irrelevant information and maintain the critical semantic information for the downstream tasks. Here, we also provide some benchmark results. We optimize the pre-processing module for the object detection task and the image classification task, respectively. We evaluate our approach on the COCO and the ImageNet dataset. Compare with the traditional BPD codec, our compression approach saves 20% bit rate on the same MVP or top one accuracy. In addition, we also evaluate our approach on different backbone network, such as FCOS or faster RCN, and the experimental results show that even if we optimize our framework for one specific backbone network like FCOS, it still works for other backbone networks like faster RCN. Furthermore, we also demonstrate the generalization ability of our approach through several experiments. For example, in our default implementation, our method is optimized for the BPD codec, but we found we can still save bitrate when we directly apply the optimized model for the JPEG compression codec. In addition, although our modular is optimized for one specific downstream task, it is general and can be used for other tasks. For example, for the image classification task, we can train a pre-processing modular, and then we use this modular for the object detection task. Experiments show that this modular can still bring better compression performance than the original BPD codec. We have the similar observation when we use pre-trained pre-processing modular optimized for detection tasks, and then we found it still works for the image classification task. All these results show that the proposed pre-processing module can be very general and can be widely used in practical applications. In this slide, we also provide some visualization results. We compare the reconstructed image from our approach and the BPD codec. It is observed that the reconstructed image from our approach can be correctly classified, while the results from BPD decoded image are wrong. At the same time, our approach consumes fewer bit rates. This result demonstrates that our preprocessing modular can provide better rate accuracy trade-off. Okay. So I will introduce another work from my group, and this work focuses on the video compression for machine vision tasks. So in the previous work, most of them are optimized for one specific task, and then they have to rely on the ground truth label, such as classification results, to optimize the whole framework. However, in the practical application, the analysis model or the ground truth label may not be available due to the privacy issue. So how to address this challenge is also very important. So in this work, we try to propose a video compression approach that can support multiple tasks without downstream label or downstream models. So specifically, we also employ a scalable coding-based framework. So however, we use traditional video codec as the base branch of the video stream, and then we introduce the semantic feature in the enhancement layer, and these features are compressed by using CNN-based encoder. The whole framework can be considered as the enhancement of the existing image codec by using semantic feature. So in the inference stage, the decoded video will be used for different video analysis tasks, such as tracking or detection. So one advantage of our approach is that the proposed semantic enhanced video compression can support multiple vision tasks. We do not need to train different model or feature extraction modular for different tasks. So to achieve this goal, we propose to use the edge information-based contrastive learning strategy to train our framework. So this is an illustration of our optimization strategy based on the contrastive learning. The positive video represents the original uncompressed video, while the negative video is randomly sampled from the training dataset. Here we have an assumption that the discriminative edge information is a key semantic information. So we choose to optimize the enhanced results to be close to the original positive video by comparing the edge information in the feature space. So at the same time, we hope our results are different from the negative videos in terms of edge information. So here we also provide some benchmark results. We evaluate our approach on three popular analysis tasks, including video action recognition, video detection, or video tracking. So, for example, for the action recognition task, we select H.264 as the basic codec, and our approach is combined with H.264. So the experiment shows that our approach has a better rate accuracy trade-off than the original H.264 codec, and it saves more than 20% bit rate. We can observe the same results for the action for the tracking or the action detection task. Okay, here are some reference for my talk, and that's all. Thanks thanks for your listening, and thank you.
Thank you. We have a few minutes for Q&As. If anybody remotely wants to raise their hand, or anybody in person wants to go up to the microphone, they're welcome to. I think we have somebody locally for a question.
Very interesting talk. I have a question. Have you considered simultaneously optimizing for the human visual systems and machine learning tasks?
Sorry.
So your talk was very interesting. It showed how to optimize for machine learning tasks. And you have a single codec that optimizes both for the human visual system.
Okay, I see. Yeah, I see. So let me first repeat the question. So you want to know how to optimize the video comparison system for both human vision and the machine vision. Am I right? Yeah.
Yes.
Okay. This is good question. Yeah. As I have mentioned in this slide, some scalable coding approach can support both the human vision and the machine vision tasks. But in our recent work, we only focus on the machine vision tasks. So I think there's some sometimes we want. I think that the reason that we care more about the machine vision tasks, and we also found in some scenario the quality of the contrast image is not so important. Actually, in our framework, for example, the pre-processed enhanced image comparison, although this framework is optimized for machine vision tasks, we find that the quality of the reconstructed image is still reasonable. It's not so bad. And although we see some decrease in the PSR metrics, if we just watched and we find that the quality is okay, so we think we pay more attention to the machine vision task.
Thank you.
Okay, thank you.
Okay, thank you very much for your talk.
Okay, thank you. Thank you, everyone.
Okay, and I think our next invited talk up is DeBarga. Let me make sure he's in the Zoom. Perfect. Let me make you co-host for a second so you can present.
Okay, thank you. Can you hear me? Can everybody hear me?
Yep, we can hear you.
Okay.
And you should have presentation ability now.
Mm-hmm.
You might have to tell Zoom to not share the audio from the presentation, so it takes the microphone.
Yeah, can everybody hear me?
Yep, we can hear you now. Should be good.
And can you see the slides?
Yes, we can.
Okay, good. Okay. Yeah, thank you, Nick. So yeah, let me first thank the organizers of this workshop for inviting me to give this talk on challenges in incorporating ML in a mainstream next-gen video codec. And I also want to wish everybody a happy Father's Day and Juneteenth Day. Okay, so this work was kind of came out of our internal discussions on how we can incorporate ML in a next-gen video codec. And a lot of the data that I'm going to present here today is based on our discussions within Google, among the Open Codex team, the research teams, ML hardware teams, and also from Apple and NVIDIA. There's a lot of activity going on in Alliance for Open Media for also looking at ML more closely. And some of the documents here are not public yet, so but I still want to acknowledge what I have heard from them. Okay, so here is the brief outline. I'll start off an introduction, go over a brief history of video codecs over the last 30 years or so. Then I'll talk about the hardware constraints of a mainstream video codec and where current ML codecs land in that spectrum. And then I'll talk about some strategies that we can use to make ML more practical for use in the mainstream codec. I'll talk about some hybrid potential research areas, like hybrid between ML and conventional coding tools, and then some high-level strategies on how we can make ML work smarter. Okay, so here is the introduction. So what do we mean by a mainstream video codec? So mainstream video codecs are codecs that have evolved in the last 30 years from standard committees like ITU and MPEG. And lately in the last 5-6 years or so, also through the Alliance for Open Media, which is an industry consortium of many companies. So here are some names of video codecs that have evolved in the last 10 years. Let's say HEVC came in 2013, HEVC and PP9 both came in 2013, then EV1 came in 2018, and in 2020 there was VVC from MPEG and also EVC from MPEG, 2 codecs. Okay, so if you look at the level of activity in the mainstream video codec community, it's actually quite active in the last 10 years or so. And actually the pace of acceleration, the acceleration of the advancement of technology has actually been pretty high. But it is getting harder to achieve gains. But one thing to remember is it's getting harder to achieve gains only if you consider complexity constraints. So if we didn't have complexity constraints, it's probably there's still 1 or 2 more rounds that these conventional technologies can be pushed. Now, on the other hand, ML-based image and video codecs, there have been enormous advances again in the last 7-8 years in demonstrating their potential. And I think that case has actually been made very adequately. There have been many new advancements in autoencoders, GANs, transformers, and so on. End-to-end frameworks are particularly interesting from a red distortion point of view because like coming from information theory, if you come from information theory background, what is always known is given a source, you can always come to a sort of red distortion function, which is the optimal or the least amount of bits you need to spend to signal that source at a certain distortion level. Now, but no one actually tells you how to achieve that. Now, it seems like learned image compression techniques or learned video compression techniques will actually teach you how to come close to this hypothetical or red distortion function. And I think in the ML community, I think there's now a transition from end-to-end image compression to end-to-end video compression, which is also quite exciting. Now, there is also some activity in hybrid frameworks, which basically attempts to replace or enhance certain parts of a conventional codec with ML-based tools. And that's where I'm going to focus on a lot today. Now, of course, the question is, given all these ML advances, how do you incorporate these advances in a mainstream video codec? Okay, so before we get into that, let's look at the brief history of video codecs over the last 30 years. So I put down some important standards that have evolved. In the last 30 years, MPEG 2 came in 1991, and it was a huge success over the next 10 years or 15 years because DVDs were using MPEG-2. In 1998, there was a standard called MPEG-4 Part 2, which was kind of it's a very interesting standard, but it was not really successful in the market because it actually expected the encoder to do a lot of things that that the encoder at that time were not able to do, like finding segmentation, very good segmentation of a video and things like that. So that didn't materialize. So MPEG-4 Part 2 was not a very successful standard. But in 2003, there was H.264 AVC, and that was an enormously successful standard. So it actually increased the compactness of an MPEG-2 bit stream by about 50%. And around the same time, Blu-rays were evolving. So people thought for a while, like now we have H.264 and Blu-ray discs coming in, so there is no need to do any more video compression. That's the end of it. So there was a lull for about 7-8 years. That is what I call is the end of the DVD Blu-ray era. But then streaming era started around late 2010s. 2000s. And then there was this open source WebM project that was started in 2010 from Google and some other companies. But then this 2013, there was the next MPEG standard H.264 HEVC. Around the same time, VP9 was released. They are roughly comparable. And then 2018, AV1 was released from another industry consortium called Alliance for Open Media. So AV1 was, at the time AV1 was released, that was the best codec out there. But then in 2020, there was another MPEG codec that evolved, that was H.266 VVC, and that kind of betters AV1 by a certain margin. And EVC was another codec, and that also came from MPEG. And in our experiments tests so far, EVC is about the same level as AV1. So now both AOM is an alliance for open media. I wouldn't get into that, but it's becoming quite an important force these days. Both AOM and MPEG are working on a next-gen codec. Now, of course, we need the gains at low enough complexity. So that's the goal. So there is an MPEG AOM codec, a new MPEG codec that is expected in maybe 2 years' time, and maybe a new MPEG codec expected in another 5 years' time. Now, in a typical standardization process in these mainstream codecs, there is always a constant tug of war between the coding efficiency of a tool and the hardware implementability and even software implementability. Okay, so every tool that is proposed is scrutinized very meticulously for every computation, every multiplication that you do, and so on. Of course, divisions are not even possible to do, so that's a different question. So and then and all unnecessary computations are eliminated. But at the end of it, every standard would advance state of the technology by about 30–40%. So you may get maybe 30 to 40% more compactness over the previous generation codec. But it also advances the state of the hardware. So it sets the stage for the next gen hardware that goes into many mobile chipsets and DSPs and so on. Okay. So that's how the mainstream video codecs have evolved so far. Now, let's look at the characteristics of what we call by a mainstream video codec. So I think it's really the decoder that is the most important here. So the decoder should be available everywhere, should be cheap or free, should support decoding either in hardware, software at desired throughput. And for today's, according to today's trends, the throughput for video is 4K 60 or 8K 30. Okay, it's becoming less and less. For images, okay, let's talk about images a little bit later, but let's say should have a very small hardware footprint. So the silicon area is very important especially for mobile chipsets. So people are very conscious about how much silicon area a video decoder would use. And of course, it should be very low power. Now, there are two predominant applications of video today. One is video on demand, like watching YouTube or Netflix and so on. So in those cases, the encoder can be much more complex because you can do offline encoding. And for that, software encoding may be better because software encoding can actually search better this space of this huge space of parameters that an encoder typically needs to search. But there is a transition to hardware encoders also underway. For for services such as YouTube or Facebook, where we get a lot of user-generated content. Just the sheer volume of videos that are uploaded and needs to be encoded means that hardware encoders at some point becomes much more cost-effective to use. Now, of course, there's the other application, which is real-time communication. For real-time communication, of course, there is a very stringent requirement for encoder and decoder together, and there can be various architectures, like both sides, encoder and decoder, can be doing software encoding and decoding, or maybe the decoding only happens in hardware, but the encoding happens in software, or both can happen in software and hardware. So there are many architectures for that. Now, of course, for hardware encoder, there is the budget in the silicon is actually higher than a decoder. It's typically about 5 to 10x higher than the decoder. Okay. Now, just to complete the discussion here, you remember that like I talked about this this time here between 2003 and 2010, where people thought that video codec, like standard video coding, is dead because internet streaming has not started, and the amount of space that you have in Blu-rays is sufficient for very high resolution videos with H.264. But people had to do something. So there's one of the things that people in the video coding signal pricing community were doing was what is referred to as distributed video coding. So here the idea was to actually reverse this complexity paradigm that I talked about before, which means that the encoder can be complex, but decoder has to be very simple. That's the standard paradigm. In a reverse complexity paradigm, the idea was to make the encoder very simple. That means it can be very simple, like very all intra operations with little or no motion. However, the decoder can be very complex. So decoder can actually be used for offline decoding of video that you capture on a very small, low power device. There's another model that was talked about was you can do real-time communication where the decoder side gives you continuous feedback, and then based on the feedback, you adjust the encoding scheme. So both of these, this area of distributed video coding was extremely popular in the 2000s for a few years. And everybody who has worked on compression were actually doing this. So the main, the theory behind that was based on two information theoretic theorems. One is called Slepian-Wolf theorem. The other one is called Wiener-Zieff theorem. So the idea in a Slepian-Wolf theorem was, suppose you're doing lossless encoding of X, and you have a Y, which is most likely a predictor of X. So you could create an encoder which gives you the rate, which is the entropy of X given Y. That's the best possible rate that you can have. And this kind of encoder is very simple to achieve. But on the right, you will see a Slepian-Wolf encoder where this connection of Y to the encoder has been removed. And the theorem says that even if you didn't have Y at the encoding time, you can actually do just as well. So you can actually create a Slepian-Wolf encoder and a decoder, which can also give you a rate which is the same as the conditional entropy of X given Y, even though Y was not available at the encoder. The only thing that you need to do is you need to have the joint statistics of X and Y known, and the decoder needs to be, of course, more complex and to figure that out. Okay. And similarly, in the lossy case, there is this Wiener-Zieff theorem, which also says the same thing, that if you want to compress X given Y at a distortion D, then the best rate that you can achieve is a so-called rate distortion, conditional rate distortion function of X given Y at a distortion D. And that's the best you can achieve. And the Wiener-Zieff theorem says that even if Y was not available at the encoding time, you can still do just as well. Now, there was a huge amount of interest in the source and in the signal processing community on generating practical Slepian-Wolf and Wiener-Zieff encoding schemes, and it was a combination of source coding and channel coding and side information generation. And looking at all the advancements that has happened in ML over the last 5-6 years, I feel that this is one area where ML can actually be very useful. It's actually a niche area because reverse complexity, the application areas are still niche, but it's still quite an interesting area to look at. Now, moving on. Now let's look at the hardware constraints now in a little bit more detail. So the constraints that I'm going to talk about has a time horizon about 5 to 6 years. So as I mentioned, the AOM codec expected in about 2 years. And new MPEG codec expected maybe 2027, around that time. Of course, this is quite speculative, so we don't know how MPEG works. We do know how AOM works, and we are working towards the next gen codec in about 2024 timeframe. And so all the constraints that I'm talking about here are only valid for the next 5 to 6 years. After, maybe if we look at 10 years time, all these things may have changed. And also these constraints are for mainstream level deployment. So there could be certain niche applications or niche standards where these are not valid. Okay, so this is just to set the stage. Now let's look at the state of hardware video decoders. So the one thing to realize and that we realized quite recently, is the current thinking of all hardware companies that make video decoders is that they cannot assume availability of external GPUs or TPUs and so on that can perform outside of the coding loop ML operations, while the rest of the processing is done in fixed function hardware. So this is I have one this document is not public, but it was discussed during in the AOM working group. And there was similar thinking from Apple and NVIDIA. Like NVIDIA is quite big in GPUs, but I think their thinking also is like for the next gen codec coming in next 5 to 6 years, they still prefer dedicated hardware IP for video decoding. Okay, and now of course another important factor is the throughput requirements for that decoding device, and the current trends say that it has to be at least 4K 60, or maybe 8K 60, or at least 8K 30. Now, the silicon area needed can be lower if throughput is lower. So if you're only doing images and we don't want need to decode images too fast, then the throughput can be lower. And if throughput can be lower, then the silicon area can also be a lot lower. But let's say but not by a lot, because all the applications of images that are evolving today, actually only in niche cases you can actually get away with very slow decoding for images. Okay, so it's because if you are browsing, let's say the title list from Netflix, you want them to really decode really fast. Okay, and what matters most is really in the amount of raw computation needed. So there are many different factors here that I don't know about myself, like memory, bandwidth, RAM size. They're all very architecture dependent. But in the end, what really matters most is the amount of raw computations needed, because we cannot use dedicated GPUs, TPUs for video decoding. Okay. So if there's only one thing that the community can focus on, is this amount of raw computations. Now let's do some back of the envelope calculation on what those numbers really are for a codec today. So let's anecdotally, let's take AV1, which is that the full AV1 decoder needs lower ops per pixel than a mobile net V1 network. And it's very hard to do an apples to apples comparison in terms of ops per pixel. But let's say if we did that in terms of the silicon area, it comes to less than 4K max per pixel, max effort to multiply accumulate operations per pixel for every pixel that is decoded. Now, for a next-gen codec, from one generation to the next, usually there is a budget for increase in decoder silicon area, and it's usually that budget is about 100 to 200%. So it doesn't increase by more than 2x or 3x from one generation to the next. And of course, you need to get a bit rate reduction of about 30 to 40% over the previous generation. So based on this numbers itself, you can see that for every 1% bit rate gain that you can achieve in a codec, you can have at most about 100 to 200 ops per output pixel that you can afford to use. Okay, and this is actually a quite lenient estimate, because there are many overheads that you cannot avoid, and if you take those into account, the real number that we hear from the hardware groups is more like 50. So you can use at most 50 ops per output pixel. Okay, this is very rough math, but you get the general idea of what the current state of hardware decoding is. Okay, of course, for a hardware encoder, it can be 5 to 10 times more in silicon area than the decoder. And historically, the encoder also increases 10 times more than the previous generation. So here's a slide I'm borrowing from my colleague David Minan's presentation in ICIP 2021. current frontiers in neural image compression. So here he compared different neural image compression schemes. You see, this is the PSNR, and these are the levels of AVIF, BPG, JPEG 2000, and so on. And then on the horizontal axis, you will see flops, floating point operations per pixel, and these are in thousands of pixels. Now, flops is not exactly the same as max, but roughly you can say a flop is about twice that of Mac. Okay. Now you see this is the range where most of the places where they actually beat the standard codecs today are. Like VVC is not shown here, but it's probably around 34, a little more than 34. It's about 100 to 1,000. So this is what we have seen so far. The learned image codecs can have max of about 50 to 500K max per pixel of computation. Learned image codecs with GAN loss can be substantially higher. That's what it seems like, about 500K plus. Learned video codecs possibly higher, because it actually has to do some equivalent of motion on the decoder side. So you see there is from this number 50 to these numbers 50, 500, and 500K plus, there's a huge discrepancy, about 500 to 1000x discrepancy. Now, of course, does that mean that we always have to get to 550? No, because there's always this constant tug of war between the technology and what can be supported in hardware. So we really don't need to achieve 50 right away, but at least there should, to just even start a conversation, it has to be within sub 1K. That's what we feel. Like if we start off with something that is less than 1000 max per pixel or 500 max per pixel, then I think there's some negotiations with hardware teams and a lot of like innovative ways of implementing things that can be brought to bear. But then I mean, if you start off with something that is 100,000K, there is not even a conversation that can happen. On the other hand, the mainstream codecs do need the gains from ML advances, because conventional codec development is getting to be tedious, and we have been finding special cases and special cases of special cases like for many years, but that has its limitations also. So even though the complexity requirements relax, still it's a tedious process, and ML can give you ways to find things in a much simpler way. Okay, again, from the same presentation. So I adapted this and I added this thing here. Like here, the idea was to show that to really be beneficial, you need more focus on methods here, which achieve much lower flops, but gives just as well as other neural codecs. But for mainstream level deployment, it actually has to be here, much smaller than, much lower in flops. Okay, so now how do you achieve that? Like how do you go towards this practical MLs that can actually achieve this mainstream level deployment? Of course, it's okay to have incremental gains in incorporating ML in a mainstream codec pipeline. So mainstream codecs are really snapshots in time. Nothing changes when a standard is done. The state of evolution of hardware and video codecs is often incremental. So even if a pretty simple but substantial ML tool gets into a mainstream next-gen codec, it makes it much easier for a much bigger tool to come up in the next edition. I'll give an example. Let's say transforms. In the 2000s, people could only use DCTs and trigonometric transforms, which have butterfly implementations, which are efficient butterfly implementations. But in today's codecs, with the advent of VVC and all of that, I think because there are some non-separable transforms that have been used, so that constraint has now gone. It took 10 years, and we get the gains because of that, but it's an incremental gain. But still, it helps to set the state of the technology for the next edition. So in the next edition, when you're working on the next gen AOM codec or ECM or whatever, then we can actually assume that we can use much bigger transforms and not be constrained by only using trigonometric transforms. So this is actually quite normal in the way the state of the technology evolves. So even a cost-effective ML tool that gives only 1 to 3% bit rate gain is actually okay, but we have to make it cost-effective. And I do think that if you look at at the signal processing side of things, there's a great deal of room for innovation in these lightweight models. So there's a lot of the work that has been done in mainstream codecs is at very low ops per pixel, and then a lot of work being done on 100K plus ops per pixel. But in between, there are other sweet spots that are not being explored enough. Some high level ideas. So like, I think what we do need is some kind of a RDC metric, rate distortion complexity metric, that incorporate model complexity. So we can use a score that uses model complexity as a parameter in addition to BD rate. And that will slowly move the community to looking at lightweight models. Perhaps it could be a new track for CLIC 2023. Of course, we do need a better understanding of what exactly ML model is doing to reduce the complexity. And I think it does make sense to look at a conventional codec pipeline and see where ML can be substantially beneficial over standard signal processing methods. For instance, prediction, nonlinear transforms, in-loop filtering, and so on. You can also look at things in ML where you work on a smaller subspace. Like we don't have to work on all this pixels, but maybe work only on the high frequency part and let the low frequency part be handled by traditional codecs, or vice versa. So there are many ideas that we can explore, but let's look at a standard conventional codec pipeline. So typically what you do is you code frames one by one. And when you code a frame, you have a reference frame stored that is already available to you, which has other frames that you previously decoded or encoded. And then you use the previous frame store as well as this area around a block, which is a causal area within the current block. And then you can use all that information to get the best possible predictor for any source block. Okay, and then once you have a predictor for it, you signal the prediction information, whether it's interprediction, what mode, and so motion vectors, and so on. And on the other hand, once you have the predictor, you take the difference, you get the prediction residue, then you do a transform, quantization, and then the decoder side, you kind of do the inverse of that, and then add it back to the predictor and get the reconstructed block. Now, once you do reconstruct the block for every frame, then you have a reconstructed frame. And then there is an operation that you can call as restoration of the frame. It's called in-loop restoration because it's done within the codec loop. So once you restore the frame, and restoration of the frame means deblocking, debanding, and many other things that people have done in this space. Once you have an output frame that comes out of that, you will actually also feeds it back to the reference frame store to update the reference frame buffer. So this is how a traditional codec works, and there are main three components of it: the prediction generation, residue coding, and the restoration information, coding and doing the restoration operation itself. So those are the three main areas that we can look at first. So let's say if we do ML for improving the prediction. So traditionally in video codecs and image codecs, the prediction has been handcrafted, but we can actually use a data-driven mechanism to generate these predictors. There is the intra-prediction that we can do with by predicting this Z or the current block from X, which is the block's neighborhood. But you can also think of a more general purpose way of looking at it. So if you can think of interprediction as well as intra-prediction, how we can combine them, it's a more generalized view of that. Now, one area where traditional codecs have benefited a lot lately is using this multi-mode prediction schemes. So you don't really have just one predictor that handles everything. You have, let's say, tens and even hundreds of predictors, and then the encoder searches all of them and signals the best predictor to the decoder side. Now, if you do a data-driven design for that, suppose you generate data and try to design those predictors, then there is a lot of interesting problems that you can solve in unsupervised clustering of these modes and actually evolving the modes that would give you the best bang for the buck. So this is one area that people can look at. Another area is this nonlinear residue coding compression scheme that I mentioned. So this is a typical schematic of a learned image compression pipeline, a very simplistic view of it. Okay, so you have the X, then you have encoder network, you have quantizer, which creates, then you do entropy code and send some data out in the bit stream, and then you have a decoder network which expands from the bottleneck and provides an output. Now, if you use it for coding on the prediction residues, a naive way of doing that would be just using y as a predictor, and then you take the difference, and then you train a learned image compression scheme for the prediction residue itself. So it's become sort of like a nonlinear transform as opposed to a fixed trigonometric transform or a non-separable transform and so on. Now, of course, you can think of this as a little bit more general. You have a little bit more general view of that. Excuse me. So instead of actually doing just a difference, you can think of the X and Y going into one network. And then it's a two-channel network, which creates this bottleneck, and then you send the data out. And then the same Y, which is the predictor, is also used in the decoder network as is. And then, so that's sort of like a generalization of this autoencoder neural network. And we can call it an autoencoder neural network with side information, and some other people have called it a conditional autoencoder, which is sort of like a generalization of predictive coding, where you only code the difference. But here, it actually, you can use more structure from Y and X in a better way to do something better. Now, if there is one area where I think it has the biggest potential of using ML in a traditional codec pipeline, it's the in-loop filtering. And a lot of people have done work in this space. We have done some work on AV1, for instance, and we can get about 3 to 5% bit rate gain with a network that has about 15 to 40K flops per pixel. I think VVC in JVET, it has been shown that you can get up to 6 to 8% bit rate gain with a much bigger network. Okay, now of course we need to focus on looking at sub 1000 flops networks. Okay, some experiments that we have done based on some of our the findings from the hardware constraints is that if we use a model with only 600 max per pixel, the bit rate gain can drop to 1%. So a 20K max per pixel network has about 3% gain, but then if we use a very small network, you still have 1% gain, but it's not sufficient enough. So of course, there's a lot of work that can be done in using novel architectures with low operation count that can come closer to standard image processing methodologies. Another area that is quite interesting is in-loop super resolution within a video codec. So you could downsample, compress, and upsample pipeline. You generate a pipeline like that, and you can downsample an image by a factor of P by Q, compress, decompress, and upsample. This is without any other signal processing if you just do a good linear filter for downsampling and upsampling. Now, of course, you can enhance this by having a post-CNN after the upsampling operation. You can also have a pre-CNN before the compression. So you can design the pre-CNN and post-CNN and train them jointly. That will give you most likely better results. And of course, if P and certain values of P and Q, especially if Q is 1, so if you're doing 2:1 or 3:1, then the pre-CNN and this downsampling operation can be combined. So that you will actually learn also the filter that is used for downsampling and upsampling. So this area has quite a bit of potential, and we did some work in the second part here, where we just use a post-CNN. And this is one example from, let's say, the crowd run sequence. So each of these have different ratios of downsampling and upsampling. This is for 2:1, 3:2, 4:3, 5:4. One thing to realize is most of the work in this space in academia has focused on the 2:1 case. But if you look at all the curves here, the top curve here is the full resolution encoding curve. The bottommost one is if you just code it at lower resolution. And the one in between is what you get by using the post-CNN. Of course, you see that the post-CNN will improve the performance substantially. And these numbers that if you compare these two curves, let's say the downsampled one and the downsampled with the post-CNN, you can get substantial bit rate gain between these curves. But this is actually a fake gain, because for in a real codec, what you really need to focus on is this part here, at the very lowest resolution or the lowest bitrate parts where there can be an overlap. Okay, and if you look at the different resolutions that you see, if you see 2:1, after the very lowest bitrate points, there is absolutely no hope for it to actually beat the full resolution encoding curve. So what happens in the higher quality end actually really doesn't matter. What really matters is really the lowest resolution end. So when you compare, we really need to compare the convex hull of all the possible resolutions that are supported, and then compare that with the full resolution curve. So that's where it makes the difference. But on the other side, it seems that in this super resolution kind of schemes, you can get away with very simple models. It seems like these are the results with a very simple 2000 parameter model with 2K max per pixel. So these are actually very simple models, and if you increase this more, you get bigger gains. But this is actually and it seems like the knee of the curve, that as you keep reducing the model size, model complexity, can be pretty low in the super resolution case. Okay, so now the last thing that you want to talk about is some strategies to make ML work smarter. So like if you have a deep neural network, then not all layers of the network need the full even 8-bit or 16-bit multipliers. You can actually get away with 4-bit multipliers or even 2-bit multipliers in many of the internal networks. So there is a QKeras a project that was recently open sourced, and it's actually a quantization layer, quantization aware training layer that sits on Keras, and that can be used for doing training based on quantization. So you can say that, okay, certain layers you can just use only 4-bit multiplication, and that can actually help a lot the computation and hardware, the silicon area. Going hand to hand with that, there's another from the Google Cloud platform. We have another tool called Vizier that you can use to actually search the parameter space. And this is especially important if you are doing quantization aware training, because you need to search among different options for your bit depth, which is the best, or the number of layers, which is the best. So the Vizier can be very useful for that. Some very general ideas is like if you use more processing at lower resolution, it's actually better because that reduces your operations. So UNet type architecture is preferred. And of course, we also see that if you're doing like in-loop filtering kind of work, if you go down to too lower resolution, then it's not very helpful. It actually can be reduce your gains. So there's a lot of work that can be done in actually figuring out good architectures that can give you the most gains without a lot of computation. There you can use origin symmetric kernels, which is natively not supported by TensorFlow as far as I know, but you can, a lot of the work that has been happened in the signal processing community assumes there is, like if you're doing winner filters and things like that, we assume symmetric kernels, and symmetric kernels origin symmetric kernels can do just as well as asymmetric kernels. But if you did origin symmetric kernels, you reduce multiplies by a factor of 2. And then there are some other thoughts, like some initial layers of a neural network may actually be replaced by integer filter banks, like maybe hard integer wavelets 5.3, which are much simpler to implement than multiplies. Okay, another thing is all the decoder constraints that I mentioned here only refer to the decoder side. So the decoder side is extremely constrained on the silicon area, but less so on the encoder side, because there are a lot of VOD applications which you can get away with a much heavier network. So if you have a learned image compression pipeline, as shown in the schematic here, you can make the encoder side a lot bigger and make the decoder side much smaller, and that can actually help you to keep the coding gains, but make also the decoder pretty small. In a way, it becomes similar to vector quantization. Vector quantization is also, of course, the encoder can be very complex and all that, but the decoder is a simple lookup operation. Also, in this downsample, compress, upsample pipeline, if you have pre-CNN and post-CNN, again, the pre-CNN, which is part of the encoder, can be bigger, but the post-CNN, which becomes part of the decoder, can actually be much smaller. So you can change these balances to give you a better trade-off between decode complexity and encode complexity. Another thing that is quite interesting is to actually evolve switchable networks. So a switchable network is on a common hardware. This is what we mean by that. So let's say typically in a codec, image codec or video codec, it's not that we have just one like one mode for everything. Actually, we have hundreds of modes for everything, and every mode can invoke a little bit of different processing. Now, and the encoder does the search and actually signals which one is the best, or which mode is the best. Now, following this similar thought, for compression purposes, the encoder can do a lot of hard work to figure out. Let's suppose you have 100 different CNNs, neural networks to choose from, and the encoder may choose, okay, let me choose one of those 100 and just signal that in the bit stream, which one is being used. But when the decoder receives that input, it just uses that particular CNN to do the inference. Now, if you had a common hardware where even though you have 100 CNNs, maybe all of them use the same network architecture. So the hardware itself for doing the computation can be the same, but the weights can be different from each of those different networks. So that way we can actually sort of classify the thing, your data set, in a way where it actually makes the inference process much simpler. Okay, so this so there are some things that we are trying here on actually having a common architecture for same resolution and super resolution in loop filtering with the same model architecture. Now, but the actual model parameters are downloaded on a frame by frame basis to the actual hardware. So the hardware itself can be common, but we can aggregate the gains that come from each of those subclasses. And so the way we choose the models could be a combination of this transmit index, quantization parameter, the amount of resolution reduction that was done, and so on. Now, one thing to remember is video chipsets are already designed to store large amounts of memory. Like they're designed to store, let's say, 16 or 8 different frame buffers in the frame reference frame store, and those take a lot of memory. So in comparison to that, and with simple enough models, the amount of storage that is needed is not at all high. So this is actually doable in practice. I mean, this is one area where we can negotiate with the hardware teams to actually get them to implement it in this way. So the idea is to have a common hardware. Each instance is low complexity, but the model can switch at a certain interval, at a suitable interval, maybe at a frame level or even a tile level. And of course, to designing these CNNs in that way needs some sort of unsupervised clustering from the data itself. So there could be a lot of interesting research problems to look at in how do you design these clustering cum training operations jointly. Okay, so that we actually come up with these classes that are really useful. Finally, you can also do things where we use what we call guided networks. A guided network is one where, if suppose you have a CNN, but you only you pre-train certain weights and layers in certain layers, but certain other layers you keep them floating. So you let the encoder choose those and signal those to the decoder at the encoding time, maybe for every frame or every block and so on. So the benefit also, the hope is that each inference instance can be much lower complexity. And we have done some work in this where we only looked at the last layer. So the last layer, so this is how it works. Like if you have X, that is your degraded source or the reconstructed frame that you want to restore, you have a CNN that goes over multiple layers, but it produces M outputs. Now these M channel outputs are then combined with weights A0 through AM-1, and those weights are actually signaled in the bit stream directly. So it's not something that is already known by the encoder, but it's actually signaled in the bit stream. So the encoder would signal these weights A0 through A1, and this neural network needs to only learn how to project X into a subspace that is most suitable. And because that has lower dimensionality, hopefully the CNN will need to learn work less. Okay, and there is the winner filter is a very standard structure that is used in for restoration of frames in images or video. And if you look at do a CNN followed by a winner filter, this is actually a special case of this generalized formulation. So there are some tricks like that where you try to marry some signal processing concepts with pre-trained networks that you can use to actually reduce the amount of work that the ML part itself does. Okay, so that brings me to the end of this presentation. So to conclude, mainstream video codecs further advancement is becoming tedious. It's true, but it's still possible if we didn't have complexity constraints. It's becoming tedious because people always think of complexity constraints. Now, for a mainstream video codecs, you have very stringent requirements on decoder side complexity for cost effectiveness. ML codecs, the potential has really been adequately demonstrated in the recent years. Maybe okay for niche applications from a complexity point of view, but in the short term, let's say in 5 to 10 years or 5 to 6 years time frame, there is a huge gap in complexity cost requirements for a mainstream deployment. And also have a suggestion for the ML research community to focus more on demonstrating potential with smaller models. I think the focus today is on too much on bigger and more complex models, but not enough on lightweight models. So we need to more focus on what can be done with smaller, lightweight models and some understanding of what the ML is really doing and bringing it back to actually reduce the computation. And also threw out some ideas of new research opportunities in hybrid ML and traditional signal processing approaches. Okay, so with that, I conclude my talk here. Probably I went over.
Thank you, Debarga. We probably have time for a couple of questions. If anybody has one in either Zoom or can step up to the mic here in the room. Maybe I have one question, and that is, do you ever see a future for fully neural methods being used?
So
you see the future
yes.
being hybrid for quite a while.
Yes, so I think in the next 5 to 7 years, very unlikely. I mean, as you know that we have been trying to get some ML tools in AV2, for instance, but it has been, I mean, the negotiations on the hardware side has not been very hopeful on that because of these constraints that I mentioned. Now, in 10 years' time, things can be different. But I do think that there is some, if we already understand certain things in the signal processing way, let's say certain things you already understand and know how to use, then probably throwing ML and adding a lot of computation at it is probably not the best option. So you can actually learn from what has been done in the past and just use ML in only certain cases where traditional signal processing tools don't work well. I think that's the right approach. Yes, but of course there is, if you have a full end-to-end solutions, then what happens is you can actually, some of the traditional work that today's codecs are doing, you can take that out and replace everything with a full ML codec. But then that number has to be small enough. The number of operations that you are doing has to be small enough and still be giving you a generational advantage. So that's the technical challenge. Yeah.
Yeah, I think that makes sense. I think we had one question in Zoom.
Yes.
That is, hardware implementations today cannot assume availability of external GPUs, MPUs, DSPs. What do you mean by this?
Yeah, so this is the thing that we recently learned from Google's own hardware teams, as well as from Apple and NVIDIA. I think the current thinking for the next 5 to 10 years is like, if you in a decoding hardware, it has to be a separate decoder hardware IP. So they cannot actually offload a lot of the work to an external GPU that is outside the video IP and do some work and bring it back. So that requires a lot more architectural changes that are not possible to support in the next 5 to 7 years. So and this also was corroborated by Apple. Actually, Apple's numbers is actually probably the most stringent. It's much lower than 50. NVIDIA maybe a little bit more, but it's still like, even NVIDIA who make GPUs, they think that they can, for video IP, they still need to use, for the next gen codec, they still need to follow the traditional method where the overall, the silicon area of the entire video decoder needs to be substantially small. So if you add a GPU within that, then it becomes much harder. Yeah, in terms, much bigger in terms of silicon area.
And I think we have one more Zoom question from Gang Wu. Do you see any difference in lossy and lossless in terms of what you presented today?
Okay, so yeah, so in terms of like a lot of the work on let's say nonlinear transforms and things like that really doesn't make sense for the lossless case. Now, for the lossless case, of course, what matters more is generating very good predictors. Yeah, so and of course, a transform itself can be nonlinear also and still be fully reversible. But I still that's probably going to be a little harder to do. Yeah, I think there's not much of a fundamental difference, but in the image video coding community, it is mostly lossless. Lossy is mostly lossy. Lossless is still kind of like a niche area which are used for archival and things like that. So our focus has primarily been on lossy compression.
Okay, thank you again, Debarga. We're going to take a 15-minute break and then move on to the datasets challenge and rating task by Luca and Ross. So yeah, please use this time to do what you need to do.
just say I would. That's it.
Okay.
Okay.
Okay, we are back from break.
Hello, everyone. I hope you can hear me. Sorry. I'm Luca, and today I will be talking about the image compression challenge. So the setup and the results. So as Nick mentioned before, and like the previous years, we decided that the main discriminator for the image compression challenge would be human evaluations. And why human evaluations? Well, as usual, you can see, I hope you can see at least, I don't know if you can see it neither in person nor on Zoom, but maybe. You can see that you can have images that have the same bitrate, such as the two images in this slide, in which while one image has a much more accurate, a much higher score according to standard objective metrics, in practice, humans tend to prefer the other image. And in this specific image, for example, you can see that the whole texture of clouds in the distance is completely different between the two images, and the aspect of the umbrella, I guess, has also changed. But this is something that subjective metrics don't capture. That's why we still do human evaluations. Sorry? Yeah, that's a problem. Yes, if you look at it on a computer screen, you see the difference. Presentations, Zoom meetings, you know, that's just, yeah, it's hard to do these things over a big screen. Anyway, the general setup of the evaluation is the same as the last years. We release a test set that is released after every participant freezes the code and the model. And we need to figure out, you know, since we have multiple participants, multiple methods, it's not feasible to compare all the possible pairs of images and codecs to each other. So we had to come up with a smarter method, which is the same thing we used the last years. So by now it's tried and tested, I would say, which is basically to ask the raters to sort the images fundamentally. And I will go into more details of how that works. But before that, let's talk about how the test set was designed. Once again, this is identical to the procedure that was used in the previous year, and I think even in the years before. Of course, it was done this year, so the results, the selected images are different, but they were obtained with the same procedure. And there are, of course, many aspects to keep in mind when selecting a test set of images. One is we want the selection to be fair. We don't want to only show black cars in the test set, because that would be problematic. Let's leave it at that. So we need different types of scenery, different skin tones, and they don't need to be, you know, all, I don't know, red images, for example, because we'd want to test a wide variety of settings for the compression codecs. So the question then is, how do we find such set of images? In particular, because we are humans, and if we try to select images, it may happen that some of our own biases get introduced in the picture. So the procedure that was used last year and was used this year too is the following. We used Unsplash, as it is a website that offers a permissive license and allows searching by tag the posted images. Images were searched by location, and so basically selecting a number of countries from each continent. And from each search result, we selected a random sample of the images that were returned by Unsplash image search. Of course, this is not perfect. For example, usually people that post images on Unsplash are photographers, and photographers are not all of the human population. They're a small fraction of the human population. They're not, for that matter, a big large fraction of all the human photographs are taken by photographers. But, well, and another problem is, of course, that in some cases, post-processing was applied to the images, which, again, is something that's hard to control for in this setting. But one thing that we could mitigate is the images that are available on Unsplash are already compressed using JPEG compression, and to remove or at least attenuate the effect of compression artifacts in the original image, we downscale the images by a factor of 2 to try to compensate. Perfect. So the end result of this procedure is that we obtained a reasonably varied set of images for this compression, which we believe avoids biases. A downside is that we don't have so-called canonical test images. For example, images that we know are problematic if in the loop there was a codec that used 420 comma subsampling, or I don't know, an image that is problematic if the color representation has problems representing reds or things like that. We have no such concept of, images that figure out specific things, but we also don't believe that's necessary for this specific challenge. So perfect. So again, same as last year, the way the images are used are that raters are presented not with the full image, which is typically a full HD image, I believe, but they are presented with a crop of the image. Why a crop? Well, there are multiple reasons. For once, you choose first you can't show 2 full HD images on most displays because they just don't have enough pixels. So you need to show a smaller image, and you could decide to downsample all the images to sizes that fit on the screen, but then that changes the compression task because images that have a different scale of features have different compression characteristics. So by choosing a crop and by letting raters choose which crop to give their final evaluation on, we basically allowed first to actually see the image on the screens that are available to the raters, and second, we allowed the raters to focus in the sense that it's easier to reach a decision when you have a smaller image compared to reaching a decision over a larger area. And just by doing more evaluation, we can compensate for the fact that they don't see the whole image at the same time. Allowing them to choose avoids situations where this crop is selected in which no difference is visible, and so the rater doesn't know what to do. So this is the interface that was presented to raters, and I'm sure you're not going to see a single difference between the first and the second slide here, but you do. I mean, apart from image 1, image 2, that should be visible, but so the task of the rater is to select which of the 2 images on the right side is more similar to the image on the left side. And if they can't find a difference, they are allowed to select a different crop and proceed from there. So, okay, now that we have the results from these comparisons, I believe we ended up with 50,000 comparisons. Then the question is, how do we obtain a score for every method? And since this worked for the last 2 or 3 years, we just continued doing the same way. We computed an Monte Carlo ELO ranking, which was used in the past competitions, which is basically a simulation of competition rated with the same scheme that is used for chess ratings. where simply we take every single comparison as a two-player game, assign a score to the comparison, and update the rating of every codec after this. What is new, however, is that this year we decided to compute the ranking for all the images, sorry, for all the methods and all the bit rates in particular at the same time, which is interesting because, for example, it allows us to do comparisons between methods at different bit rates, which is something that you cannot do if you just do a ranking per bit rate. Of course, another decision that needs to be made is that since we are evaluating 3 bit rates, we obtain 3 ELO scores for every participant. So how do we decide the global rank? I mean, you will see from the results that it didn't actually matter how we decided the global rank in this year specifically, but the decision we went with was to choose the harmonic mean of the rank, not of the scores, of across all the 3 bit rates. Finally, final piece of information about the test, the setup. Let's talk about data quality. This is something that we added this year and aimed at, figuring out raters that were not giving very good quality answers. So what we ended up doing was, for every rater, we considered sequences of contiguous ratings of images that were not separated by more than 15 minutes of breaks, and consider each of those as a session for that rater. Within a session, what we had a set of gold questions, which were questions of the kind out of A and B, which is more similar to A, which is something that has a very definite correct answer because 2 are identical and the other one isn't. And we decided to discard all the raters that didn't achieve more than 80%, that achieved worse than 80% accuracy in that section for the gold questions. Another data quality factor, which is more of the try to detect double clicks or distracted raters than trying to detect raters that are not doing a great job, is that the rating UI forces the rater to spend at least 1 second per comparison and to flip between the 2 images at least 3 times. These are the parameters we used last years for just we used last year to discard ratings. This year we just decided that we don't allow raters to not flip at least 3 times or not wait at least 1 second. Okay, so some data out of the experiment. First, on the setup that was used by the raters, you can see that most raters were using a 15-inch laptop, with some of them using a 13-inch laptop, which is probably not the best screen for looking at images, but well, at least they did manage to reach 80% accuracy on the gold questions. So we have some confidence that the results made sense. Most raters were in a well-lit environment. Apparently, no one was in a dark environment. And finally, raters were looking at a wide variety of distances from the screen. Some of them apparently at 20 centimeters, which is interesting, but if they were using a 13-inch laptop, that's also understandable. But yeah, so as you can see with this kind of comparisons, especially with crowdsourced comparisons, the environment and setup can be different. And I believe Ross also will have some things to say about how to do things in a how to do subjective evaluations in a crowdsourced environment. Okay, so now to the part that I'm sure is more interesting for everyone is the results. You can see here the scores, the ELO scores that were achieved by each method. And there are a few interesting things to note, I would say. One thing is that at the highest rates, it's interesting to see that the best neural codec is not just better than everything else, because of course it's the best neural codec. So yes, but it's also interesting to see that for example, 0.15 BPP for the best neural codec is better than twice the bit rate for the best traditional codec. And the trend continues at other. So from this, you can also see then the final ranking in particular, but also the ranking across the 3-bit rates. And you can see that for the top 3 participants, they all have the same ranking across all bit rates. So it doesn't really matter how one chooses to aggregate the different rankings. So let's now look at some, correlations. So one thing that's always interesting to do, and of course, since we also have the perceptual track, there is more information about that later, is look at how traditional metrics compare to, how well they predict the actual rankings. And you can see here that, one in general would want the correlation between the ELO score and the MSSIM to be positive. There is if slight positive correlation at the highest bit rates, but at the lowest bit rates, the correlation is basically 0. So once again, if we didn't know this already, I guess, but you can see that traditional bitmate metrics are not particularly good at evaluating compression performance, especially when generative methods are involved. What's more interesting and different from all previous last years, as far as I understand, is that usually we also see a positive correlation between the running time of the codec and the score that the codec obtained. This was, yes, there was a positive correlation. However, what's, I think, very interesting, and I assume we will hear more about how this happened later, you can see that the top ranking codec actually got, I think, the lowest running time of all the non-traditional codecs that were tested. Not only that, this is hard to see on this plot, but you can see that this codec was actually faster than VTM, which is a traditional codec. Now, of course, there are usual caveats about VTM not actually being the reference decoder, not actually the fast decoder. But still, especially in the context of what the Barga said before about needing more balance between computation and bigger models, this I think is a very interesting result. Okay, so that's that for the image challenge. As far as the perceptual metric challenge is concerned, well, we can see that there were a lot of submissions. And officially, we rank the submissions by accuracy. You can see we also tried to compute the ELO scores that would be assigned to every codec if we had we replaced the score actually obtained, like the judgment actually made by a human, with the judgment made by the perceptual metric. And we computed the Spearman rank correlation and the Pearson correlation between the ranking obtained that way and the ranking obtained by the actual human comparisons. And you can see that at least for the top 3 positions, accuracy and both correlation coefficients agree on which the 3 best methods are, which is always reassuring. You may be wondering what's the accuracy of human raters in this slide, because I mean that's the accuracy of human raters against human raters, which one would hope to be high. So this is basically the score assigned. So for every comparison between a pair of images and codecs, between a pair of methods for a given image, we took the fraction of humans that answered one way compared to the fraction of humans that answered the other way. And the number we report here is the average of the square of that fraction plus the square of the complement of that fraction, I believe, which, unless I got my maths wrong, is the expected accuracy if every rater were to answer randomly with that probability. So it's basically a measure of self-consistency within the set of human raters. And you can see that, while we certainly, most of the metrics we have are certainly better than the standard traditional metrics, there is still some gap to be between metrics and humans that mean probably even also next year we will be doing a subjective evaluation. So that's all from me. And now I'll leave it to Ross to explain for the video track.
Okay, so I'll talk a bit about the video track evaluation. I guess I'll first talk about a new crowdsourcing platform that we developed at Microsoft for this task. I'll talk about the validation of that platform. This is an open source platform that everyone can download and use. And then I'll give the results of the video track. Okay, so I guess first of all, as everyone probably knows, lab studies for video quality assessment are the gold standard. Standards like P.910 have been used for decades, but they're expensive, slow, and they're not really practical in a pandemic. So what's been commonly used in many domains is crowdsourcing. The problem with crowdsourcing is you have unknown participants. They're all working in kind of random environments. They're using their own devices. There's no monitoring of it. So you have to do a lot of things to basically make these crowdsourcing evaluations as good as a lab study. And that's what a lot of this talk will be about. Okay, and this is an image of what a typical lab study would be like. It's in a very controlled environment, has a gray background, the lighting is known, the monitor is calibrated, and when participants come in, they are also qualified. They have a vision test, a visual acuity test, a color test as well. Okay, so there is, I guess, other related crowdsourcing platforms out there. The three that I'm aware of are shown here. They have a variety of different measures, but all of them include absolute category rating, which is what we're used here. We're also describe DCR as well. The main difference with this system that I'll describe here is we're the first ones to do rater and viewing qualifications and checks. We also check the hardware in a variety of ways. We check the network, and we do a rigorous test of the accuracy and reproducibility of the system. So I won't go over this slide in that much detail. This is kind of it shows the data flow of the system, but basically you set things up using scripts. One nice thing about this system is that it runs on any crowdsourcing platform. So we use Mechanical Turk. It's been ported over to Scale.ai. If you have your own favorite crowdsourcing system, we basically just use the crowdsourcing system to get raters. So it's a discovery mechanism, and for payment. All of the other stuff just runs on a service. Basically, it's an Azure service. The test methods that we use are absolute category rating, which is the most common. We also use ACR with hidden reference. We do degradation category rating, DCR, and we just added comparison category rating. Okay, so the major components are shown here in the system. Raters are basically qualified only once during the test. Their system is calibrated just once. The setup of the system is checked every X minutes, where it's typically an hour, and then the training also gets repeated every hour. We will typically organize the ratings. Each clip that we're testing is about 10 seconds long per P.910, and that we will organize them into 10 to 12 clips per session. And then as part of the qualification, we're checking for hardware network checks, including the resolution of the screen, the refresh rate, whether it's a PC or a mobile device. We do a network test as well. Okay, so as I mentioned, in a normal lab study, raters will have their visual acuity checked and their color checked. We want to streamline this, so for color vision tests, we only use 2 plates out of the typical 15 color plates. I don't know if you guys can see the differences in the color numbers here. We found that just using these particular 2 gives us about a 98% accuracy over showing all 15. And so that was good enough for this purpose. And then the visual acuity is normally done on a standard eye test chart, which we didn't want to use. So we used 5 Lando rings, which are shown here. And we got, I think, sufficient accuracy. I'll show an ablation study which shows the utility of both of these. We do have the user have to scale the size of the test image that's being shown of these rings. And the way that we do that is we just have them put their standard credit card up to the screen and just make sure that that size is the same. So this accounts for different resolutions and screen sizes. We also have them perform resolution, color, and brightness calibrations. So most of the raters are running Windows or Mac, and so there's the standard monitor calibrations in those systems that almost, I think, no one uses. And we found that when they do use this, it significantly improves the chance of them passing this test. This particular test, the raters have to count the number of squares, rectangles, and triangles in that image. And these levels are set to either 1 or 2 just noticeable differences, which we did a bunch of evaluations on. You've probably not seen them on this stuff. Okay. Are you? Kind of? Okay. It's a pretty good monitor. Okay. Another check that we do is for viewing distances. The way that we do this is we show 3 pairs of images where the images are slightly different. They're also, one of them has been blurred with about 1 or 2 just noticeable differences. And if you can't see them, then you're either sitting too far away, or your visual acuity may not be good enough. So the raters are asked to adjust their distance if it fails. Okay. For training and rating, as I mentioned, the training happens every 60 minutes. Anchoring is provided to make sure that they know what good video clips look like and what bad video clips look like. We don't tell them, what the rating is. We're just giving them these anchors so that they know what the general range is going to be. And the ratings include 10 video clips plus a gold question where you know what the answer, we know what the answer should be. The gold question can be either a really good, pristine video clip, or it could be a horrible video clip. And then there's a trapping question where we just make sure the user is paying attention. The trapping question will say something like, please select rating number 2. And that does have an impact. Okay, so to validate whether this works, we used 2 lab data sets by VQueg, HD3 and HD5. These have 168 sequences. Each of them has been rated by 24 ratings in a lab study. And basically what we want to do is just make sure, using the same data set, do we get similar answers? And we do get very good correlation on average. We got a Pearson correlation coefficient of about 0.95, and the results are shown in more detail here on both of these data sets. So we were happy that this gives an accurate reproduction of what happens in a lab. The other type of validation that we did was a reproducibility study. So it's not good enough just to do it once and show that it works, but we wanted to do this multiple times. So we repeated the similar study 5 times on 5 different days with 5 unique sets of raters. So you can track the number of raters and the IDs on platforms like Mechanical Turk. So that makes it possible. And here, the scatter plot shows an example of 2 different runs, and we get excellent reproducibility. Again, the average is over 0.95. So that was good. We also did an ablation study because we have a lot of checks in the system, and we want to make sure that they all have some utility. And this shows what the PCC is and the Spearman rate correlation coefficient is as well. If you say remove, say if users are failing all the gold clips, the PCC drops, from like 0.96 down to 0.57. If you detect raters that just do straight lining, where they're just giving the same answers over and over, those raters, we also check for that. Their PCC drops from 0.96 to 0.29. The viewing distance has some utility here. The calibration, in general, has good utility, and also the trapping questions, have utility. So this makes sure. We want to see if we could throw away any of these tests, but in the end, we kept all of them. Another check that we did is just to look at how the number of votes relate to the Pearson correlation coefficient and Spearman rate correlation coefficient. So what this shows, like the green line here, can you guys see my cursor? Right, okay. So the green one here is basically the crowdsource, I guess, correlation for, starting with like, I guess, 5 votes going, all the way up to 100, compared to, using entire crowdsource. So the knee of the curve is somewhere around 20, so you get pretty good utility. You're getting, over a 0.99 correlation to having, 100 ratings with just 20. And the Spearman rate correlation coefficient is also around 0.98. So in general, you only need around 20 ratings, depending on the accuracy level, that you want to get. And then the blue one here is doing the same thing for the lab study. The lab study, as you recall, only has 24 ratings, so the overall Pearson correlation coefficient is going to be lower. And you can also see the RMSE, keeps getting lower. And what's kind of nice here is, the more ratings, the better. It just keeps going down. I don't think I called it out, it was in the slides, but each time you do a hit, it costs about $1. So that's really the limiting factor here, is how much money you want to spend rating it. It's about 10 cents per clip. Okay, so that's how we developed the system and evaluated it. Now I'll just give the results. The way that we did the results is we first did a general round where we took all the teams and just ranked them all. We targeted 10 ratings per clip. We ended up getting about 7. And these are the results. You can see that the original was put in there as well. There's a H.264 somewhere in there as well. And I also put the 95% confidence intervals. So then this was not quite good enough for us to separate the top winners. So we did a second round. We picked the top 6 teams in both the 0.1 megabit per second track and the 1 megabit per second track. And that's what we called round 2. So the round 2 results are shown here. We did 14 ratings per clip. And you can see the winners in both tracks this way. We also did an ANOVA test to see what was statistically significant and separable. So I guess the good thing is on the 0.1 megabit per second track, things were much more separable, say on the 1 megabit track, because the quality is much harder to get at 0.1 megabits. So the top 3 teams here are all statistically significantly different, with a p-value of less than 0.01. So that's good. On the 1 megabit track, the top 3 teams are all statistically tied. So they are typically separated from the next 6. So you would need, I guess, either a lot more ratings than I did, or that I had budget for, to separate the 1 megabit teams. One thing, I guess, for future challenges, we may want to use either harder clips or do more ratings per clip to separate them. Okay, so compared to existing metrics, I computed the PSNR, MSSIM, and VMAF. These are the Pearson correlation coefficients as well as Spearman rate correlation coefficients. These are all relatively low, especially if you want to stack rank ML models based on this. So my main conclusion is that the existing metrics are not sufficient to evaluate this. I also compared ACR and DCR. DCR, the main idea is you have a reference that you're comparing it to, and the idea with DCR is it helps you to reduce the content bias. Fortunately or unfortunately, DCR gives very similar results. These are the Pearson correlation coefficients and Spearman rate correlation coefficients. It didn't change the rank order of the top 3 for each track. There were some differences later on in the list. We can't actually compute which one is more accurate. There's no lab studies that are publicly available with DCR results. If anyone knows of any, please let me know or do the analysis. DCR does take twice as long to rate after the qualifications. So you do have to pay more for that. I basically paid $1.50 per hit instead of $1. Okay, so in conclusion, the platform that I just described is in the process of being standardized as a crowdsourced version of P.910. You can download it on this GitHub account. There's a more detailed paper that's on archive for this, and we are in the process of creating an objective full reference VQA model using this data and other data. Our goals are to get a PCC and an SRCC greater than 0.95. We're around 0.91 right now, but we just started the project, so we hope that we'll get there in a few months. And then we will release this objective metric as well as all the data so that the community can use this to develop better ML video codecs. Okay, thank you.
So next up, we're going to have Alke Wiggers from Qualcomm. He is a research scientist who works in the field of neural image codecs. So we're just going to take a second to get him set up.
So this doesn't make too much noise.
I think we're fine.
Yeah, nice.
So I think you're good now. Sorry.
Cool, no worries. Right. Then I'm going to say this again. Thanks to these wonderful colleagues. And let's move on. The overarching theme of this talk is efficient neural codecs. And the reason that we are interested in these is that we want neural codecs to eventually be adopted in production-like settings. You know, move away from the sort of academic setting to more realistic settings. And I personally believe that if you are working on neural codecs, and I believe many of you are, then you should at least share this interest. I'm not saying that you should also do this deployment, because it's quite hard work, but it does highlight a couple of practical constraints and issues that you may not see if you stick to just running this on beefy desktop GPUs. We believe that for neural codecs to be adopted, this requires the codec to first of all be efficient. Hopefully it goes without saying, you want things to be low compute. Second, they should be deployable. So they should run efficiently on many different types of devices, not just on beefy desktop GPUs. And third, also perhaps obvious, they should be performant. They should outperform existing codecs in metrics that matter. And what I mean by this is that depending on who adopts the codec, the metric will actually be very different. I mean, some people don't believe in RGB PSNR, for example, and will only look at YUV PSNR. Some others may only look at VMAF. Some others may only trust perceptual metrics or their own eyes. And I'll talk about all three of these today, but mainly the first two. I'll briefly touch upon the third one, but I think it's actually well covered in the rest of this, this workshop. So first of all, let's take a look at how we can make efficient codecs. I'm going to show you a figure that you've seen before if you saw the Barks talk. And it's this very nice visualization from David Minan's, I believe, keynote at ISIP 2021. So this figure shows on the y-axis the distortion for models that reach 0.5 BPP on codec. And on the x-axis, it shows the compute, in this case, in flops per pixel, or in thousands per pixel. And now each dot that you see on this figure is one of the, I believe, mean scale hyperpriors trained by Minnen and the rest of the Google team. And each of the lines you see corresponds to a different work. And some of these are classical baselines like VTM and BPG, and the rest, I believe, are neural codecs. And what you see is that some of the methods here, while they reach very good performance, they do increase the runtime by quite a bit compared to, at the very least, classical codecs, but also to some of these best hyperprior models. So of course, this begs the question, can we do better? Can we increase PSNR while at the same time reducing compute or keeping it equal? And of course, the answer to that is yes, otherwise I wouldn't be showing you this figure. So while we're not quite in the top left where the bar graph wants us to be, we do improve PSNR to at least the same range while keeping the decode time relatively low. And I'm also very curious about newbie codec, by the way, which seems to be in sort of the same regime. So you can see that two of the models shown here, the Swin Transformer Charm and the Swin Transformer Hyperprior, both have very good PSNR, while only marginally increasing the flops and actually being less compute intensive than one of the best hyperprior models on this previous figure. So of course, I'll tell you more about this. But I do want to give you a small disclaimer with this figure. These Swin models were benchmarked on a 2080 Ti, whereas some of the works that also reported runtime, they may be much older, they may be benchmarked on different hardware, and they may not even have been optimized for speed or for compute. So I'm not saying, what I am saying is this is excellent work, even the ones with super high runtime, because it shows you what is possible in terms of rate distortion. And oftentimes you have to scale first, get the good performance, and only then you can start scaling down and make sure that things run efficiently on the device. We focus on improving the transform, mainly in the mean scale hyperprior. And to this end, we replace the strided convolutions and the transport convolutions in mean scale hyperpriors by Swin transformer blocks and custom up and down sampling layers. And maybe some of you are familiar with Swin transformers or vision transformers. I'm just going to leave it at this slide and not go into technical detail on those. Highly recommend you check it out if you want to know more. I think the key innovation behind Swin transformers is to not compute attention globally across the image like vision transformers do, but to split the image in small local windows in which the attention is computed, and then hierarchically increase the size of this window as you progress through the network. And this makes sure that the attention is not too memory expensive, and it keeps the compute fairly low. And actually, it starts to resemble convolutional classical models quite a bit, right? You have this hierarchical inductive bias, which probably is very useful for understanding images. So of course, these have been wildly successful in various settings, and we use them in the compression setting as well. What you get is a mean scale hyperprior that hopefully looks familiar to many of you, but now the strided convolutions have been replaced by these Swin transformers blocks, and the up and down sampling layers are now these patch merge and patch split blocks. Again, I'm not going into detail on those here. I want to keep it high level, but hopefully this gives you an idea of the architecture. And depending on what type of prior you used, you could use a channel autoregressive model as is visualized here, or you could keep it fully factorized if you want to be more efficient. I'm going to dive straight into performance of these models. And what I'm showing here is the rate distortion performance on codec, which of course is full RGB. And it's getting a bit difficult to see, of course, the closer these methods are. So actually a nicer way to visualize this is to show the rate savings with respect to some baseline model. So what's shown here are the rate savings with respect to VTM on the codec dataset. And the red curves correspond to convolutional models, and the blue curves correspond to classical codecs. The black curves to our new Swin transformer-based models. And what's especially interesting, in my opinion, is that at the low bit rates or at the low PSNRs, Swin transformer-based models outperform their convolutional counterparts. Of course, this is consistent across many image datasets, not just codec, and this holds for both this factorized model and the channel autoregressive model. We also investigated whether this would work for video. And to this end, we replaced the some of the convolutions in the scale space flow model by Augustin and al. From 2020. And we observed that we also get gains here. So again, it's a comparison between a convolutional SSF and a Swin transformer-based SSF. And you see that there are gains. They may be marginal, but we're only replacing a few operators. And we're not really changing anything about this architecture, otherwise, at least. So this is, of course, a good sign. It works across many image data sets. It works in the video setting. So that's promising. But what about compute? It turns out that the time to decode and the number of max are actually much lower for these Swin transformer-based models than for convolutional ones. And the time to decode is partially the conv transpose is to blame for this in the decoder. But nevertheless, this is a very reassuring sign. It must be noted, memory usage does increase. These Swin transformers, while they perform attention only in local windows and not globally, they are more memory expensive than convolutional models. But you see that for the same number of parameters, actually performance per decode time becomes a lot more manageable for Swin hyperpriors and these Swin charm models. So let's try to create a figure similar to Minen's figure. Of course, we have slightly fewer points here, but nevertheless. What we show here are 3 models at different sizes, mainly by changing the width of these models. And again, red here is a conv model and black is a Swin model. And what you see is that Swin models scale much better with increasing the number of parameters. So not only do you get more performance per Mac, better rate distortion, the y-axis here shows BD rate with respect to VTM, but also as the width increases, the runtime decreases much less than it would be for the convolutional models. Again, disclaimer, this is benchmarked on 2080 Ti's. So some of these works that you see on the right, maybe you can't compare them outright, but at least it should give you a feeling for that you can obtain good rate distortion performance, even with fairly low runtime. So summing up this part of the talk, we believe that vision transformer-based transforms are an efficient alternative to convolutional ones. And in the paper, we show that turning a conv hyperprior into a Swin hyperprior is actually fairly straightforward, that these Swin models far outperform similar size convolutional models. In both image and video compression, we see substantial gains, and that these Swin models are actually quite compute efficient, and lower runtime, lower number of max for the same number of parameters, even if their memory usage is increased somewhat. So if there's any takeaway from this part of the talk, it's that if you are interested in efficiency, consider using these in your encoder and decoder. It's not that big of a change. And more generally, it begs the question also, are there more efficient transforms that we could be using that we are not using? And why stick to, for example, fully convolutional ones? Concluding this part, of course, there's a second point here, and it's this deployable part. So we have some orthogonal work in this area about deploying neural video codecs to device and not just on desktop GPUs. We build prototypes and deploy these to mobile devices in order to better understand where the challenges really are and what issues you see when deploying. To this end, last year, we deployed a couple of codecs. In May of last year, we had an all-intra codec running on a mobile device, and we demoed this at various conferences. At the time, this was not yet 720p video, but close to it. And last, say November, December, we expanded to a video codec that run in real-time 720p video and was able to decode on device. And actually, I have the device with me, so if you're interested, I can talk to you later. And we demoed this at various conferences as well. And that is the focus of the second part of the talk. There are a couple of practical challenges that you have to address when deploying a codec to a mobile device. I think the first is fairly obvious. Most video coding architectures, neural video codecs, they are fairly high complexity architectures, and they use a lot of operators that are quite expensive. The solution to this is to develop an architecture, which in our case was a warping-free architecture, that performs motion compensation and transmission jointly. So for those of you familiar with the scale space flow model, what it does is first transmit a motion vector and then perform warping in pixel space. And we quickly noticed that doing something like that would be way too compute intensive. and moved away from it and did this jointly using simpler operators. Second, floating point operations are actually quite inefficient, and as hopefully many of you know. So we have to quantize this model. We have to bring it down to fixed point. And to this end, we used our own model efficiency toolkit, which is open source, so you can also use it. Of course, that's more generally applicable than just video compression. But lastly, we have to do entropy coding on device as well. And doing sort of old school, very old school adaptive arithmetic coding, that wouldn't work. A neural codecs output many tokens and many probability distributions at the same time. And therefore, you want to parallelize this as much as possible. And to this end, we developed a library, in-house library that performed entropy coding in parallel and brought this to the device. So zooming in briefly onto this, this architecture. So for those of you familiar with the scale-space flow architecture, like I said, what it does is first transmit motion information and then perform sort of pixel level motion compensation or warping in pixel space. So the visualization is shown here, shows x hat t minus 1. This is the previously transmitted frame, so the previous reconstruction, if you will. And there's a frame to encode xt. And both of these are fed to an encoder. This extracts some motion vector in or a latent corresponding to a motion vector and transmits it. Of course, this is decoded by some decoder, and out comes this dense scale space flow or motion vector, whatever you want to call it. And then we perform warping in pixel space, mapping this previous reconstruction x hat t minus 1 to the warped prediction. So this is fairly familiar to all of you, I hope, because this has been used in various neural video codecs already. What we end up doing is perform motion transmission and compensation jointly and fully in feature space using fairly vanilla operations, in this case, mostly 3x3 convolutions. So instead of performing warping in pixel space, what we end up doing is passing the previous reconstruction through an analysis transform, through an encoder, and concatenating this to the latents, the unquantized latents. No, sorry, the quantized latents coming out of the unquantized latents coming out of the encoder applied on xt. These are concatenated and passed through a couple of transforms still. This is quantized and transmitted. So this gives our encoder sufficient information from the previous frame in order to determine what should be sent and what should not be sent. But because this x hat t minus 1 already exists on the receiver side, we can simply reuse this information and again append this latent or latent-like feature to the transmitted information. And so some work has, I believe, referred to this as the free latent as well. The advantage of this is that we don't have this warping operator, which we noticed became very expensive. And so we can stick to sort of well-defined and then well-optimized operators instead. For the full architecture, I'm going to refer you to the paper. There's very nice visualizations in there that show the entire thing. And I do want to note there are other works that perform warping in feature space as well. We're not the ones to invent that, but for example, FVC and C2F, which a previous speaker, I believe, is a co-author of, also warp in feature space, but they still do some kind of warping using deformable convolution. So the question I have to them is whether this would be efficiently implemented on device or not. Putting this together, what we get is a two-step process. So we do perform encoding offline. I do want to be very clear about that. Encoding is a lot more expensive with these type of models because you still have to perform encoding and decoding in order to get this x hat t minus 1, this previous reconstruction. So what we end up doing is passing this through a neural encoder and using parallel entropy encoding to create some packets. These we save to a bit stream or to a database. And for this demo, what we do is real-time decoding on this mobile device. And what happens is that parallel entropy decoding takes place on the CPU and neural decoding takes place on the AI accelerator on chip. And of course, these can be nicely pipelined so that they're always doing something. There's no idle time. And what we get is 720p decoding of video on device at least 30 FPS. This on-device codec is obviously much weaker than full high complexity architectures, but it is competitive with FFmpeg X265 in zero latency mode on UVG. measured in RGB PSNR. And of course, these visualizations are also in the paper. And we provide additional results and runtimes for various demo videos in the paper as well. So concluding this part of the talk, neural video codecs can be deployed to the device. It's not easy, but it can be done. And they are able to decode video in real time. It requires a couple of things. So taking a careful look at expensive operators and operators that may be difficult to quantize. Careful model quantization, which we did using this model efficiency toolkit. And fast implementations of on-device entropy coding. Because you don't want to be bottlenecked by either the CPU or the neural accelerator in either of the stages. We will likely continue to deploy codecs to device in order to better understand what the challenges associated with them are, and to see whether we can make efficient codecs and hopefully get a bit closer to this picture that Barak sketched. So the last point, which I'll be brief about, is that we want them to be performant as well. Of course, we want to outperform existing codecs in metrics that are important for those adopting these codecs. Now, the neural codec community has mostly stuck to RGB PSNR. And actually, the results I show are also RGB PSNR for the most part. And of course, MSSAM as well. But it may not convince those working with video codecs. We know that the standards community favors BioV PSNR, and perhaps for good reason, because it does match human perception a bit more closely than the Euclidean RGB PSNR. We know that some favor other distortion metrics. We've heard many people say that they trust VMAF most of all, but perhaps because it is industry-backed, or perhaps because it's a learned metric. And we've also heard people say that they trust no metric, and that actually some of the results we just saw from the previous speakers hint that no metric perfectly predicts what human evaluators are going to say. So there's also something to be said for that. I personally believe that for neural codecs to be adopted in realistic settings, they do need to win in user studies. They need to actually be convincing. And luckily, this is now the de facto standard for the image and video compression challenges here at CLIC. Or we need a better metric. And luckily, there's also a perceptual metric challenge, which is exactly aimed at this, even if it's only for images at the moment. So hopefully I've given you a brief overview of the things we're working on. At Qualcomm, we're working towards a neural video codec that is efficient. We're developing codecs with low complexity, and we believe and we hope that there are even more efficient transforms and even more efficient prior models that obtain similar rate distortion performance or better. We're deploying codecs in order to really see what are the issues associated with these. And we published this at ACM MMSys. So if you're interested in some of these challenges and how we address them, I recommend you take a look at the paper as well. And lastly, of course, they should be performant. So in future work, we will consider not just RGB 444 metrics, and I'm really looking forward to some of the outcomes of these tracks as well. And lastly, I think many of you are doing this already, but it is worth measuring compute in your work in some shape or form, as this will also help make the case for adoption. It doesn't really matter what type of compute measure you use. Maybe it's number of parameters, which is a proxy at least for the compute. Maybe it's max, maybe it's flops. It would be great if you're actually decoding on device, of course, but maybe that's a bigger challenge. And with that, thank you for your attention. And if you have any questions, let me know. Fabio.
Thanks for that. I have a very specific question. I don't know if you have the answer, but on the swing models, have you looked at the representations these models were? Are they different from the CNN? Like in CNN, you observe that we get kind of stuff that looks like a small version of the image. Do you see similar things?
Yeah, good question. So I didn't go into detail in this talk since I thought it would take too much time. It turns out I'm actually well on time. We did look at it, and in this iClear paper, we analyze both how these latents look and what kind of correlations there are between latents, as well as perturbations of this latent space. And it turns out that these SWINT models are actually more robust to perturbations of the latent space, like masking certain channels and so on. So it looks like they are learning something that's not quite the same as convolutional models. Whether it's a better representation, I mean, rate distortion performance tells us yes, but I don't know if they are more interpretable or anything along those lines.
Thanks.
Sure.
And maybe one more quick question. So the on the entropy coding side, making it fast, I noticed that sometimes our representations get very big with like hundreds of channels.
Yeah.
Is this something you optimize there, or you are still in this similar dimensionality?
Still in similar dimensionality. I mean, I would ask one of my colleagues for the fine details of parallel entropy coding, obviously, but I think that the number of channels isn't the thing that makes this compute efficient or not. It really is about things like sparsity of this representation and how you're exploiting this sparsity. So we are still sticking, for the most part, to, I think, default choices, 320 channels for latents. For the model that we deployed, we have reduced the number of latent channels, at least, for some parts of the model.
Thanks.
Sure.
We actually had one question on chat as well.
Mm-hmm.
Are there any algorithmic changes to parallel entropy encoding, or is it mostly multi-threading and multi-core work?
Again, I would probably ask my colleague Amir about this. It really is about splitting the bit stream into components that you can encode separately, and then indeed making sure that you're parallelizing well. For algorithmic changes, I would recommend get in touch with me, and then maybe I can answer the question with Amir in the loop as well.
Okay.
Hi, thanks for great talk. I'm wondering, I'm excited about this demo you have on your phone.
Mm-hmm.
Like, how hot is it? Like,
how hot is the phone?
Yeah, when you run the decoder.
Right. It does get warm. I can give it to you in a bit, and then you can feel how warm it gets. Of course, it does get warm. It's using something the entire time. It's decoding in real time.
But I guess to be more specific, like how do you measure power usage?
We have mostly measured decode runtime, and power usage not so much, I believe. I mean, this really was intended to be a research prototype, right? Not an actual product. I think once it gets to that stage, if someone is going to build actual products, then things like power usage become much more important. What I can say is, of course, it's more expensive than a standard codec, especially if those have own hardware implementations or they're efficiently implemented on the chip. But of course, one advantage we have, we don't need additional silicon. We just use the neural accelerator and use the CPU.
Great. Thank you so much. One more slide.
I've got one more. That's okay.
Cheers.
Yeah, great talk. Thank you so much for it. Just on a question on the efficiency side and looking at the compute to measure complexity. And you mentioned the swing transformers have reduced the number of the compute, but increased the memory usage. And so my question, knowing a bit about how that also links with runtime, memory usage also has significant impact on how runtime is performing. And so at what point do you think we need to consider and take into account the memory usage when considering?
Yeah, good question. As soon as possible. Now, more seriously, yes, it's right that if you use additional memory, you will have to take that into account when you actually deploy these models. Now, these two parts of the talk were orthogonal. We haven't deployed this swing transformer-based model. But once we get to the stage of deploying swing transformers, yes, we will have to take a very careful look at memory, because it will greatly affect runtime, like you say, and which parts you load into memory and how you optimize this. It becomes a lot more important. Yes.
Thank you.
Thanks one more time.
I will give you back your.
Thank you.
Okay, we'll be moving on to some of the image track talks. Let me pull up that list here. Do we have team IMCLT2? I think they might be in Zoom.
Hi, we are here. Can you hear me? Sorry, can you hear me?
Okay, perfect. I'm going to give you present capabilities here in a second, and you should be good to present. Yixin, are you able to present?
I'll share my screen. Wait a minute.
Yes, we can see your screen. I don't think we can hear you yet.
Sorry, can you hear me now? Sorry. Oh. Okay.
Oh, the Zoom call can hear. Let's maybe try to reset this. Can you try one more time?
Okay. Can you hear me now?
Yep, perfect.
Okay. Okay, I will start my presentation. Hi, everyone. My name is Yixin Gao, and I come from University of Science and Technology of China. It's my great honor to introduce our method, perceptual image compression with controllable region quality. And our team is IMCLT2. Image compression is an important technology to reduce the resources of storage and transmission. With the great success of deep learning, learned image compression developed rapidly in the past few years. Some of them have achieved better performance than classical image compression standards like JPEG 2000, BPG, even the state-of-the-art classical codec, VVC. In addition, more pleasing reconstructions are also crucial and have spawned a lot of perceptual image compression frameworks. However, in real world, people may have different requirements for different areas in one image when making subjective evaluations. Since humans are sensitive to different image contexts, we target at building an image compression model that supports controlling the perceptual quality of different regions. Two highlights of our method are shown in this slide. First, we build an image compression model that supports both variable rate and region adaptive quality control, which still delivering relatively good objective performance. Second, image adaptive quality maps that are generated from a silency detection network are utilized to achieve better perceptual compression results at various image regions. The high-level structure of our codec is visualized in this figure. Our compression network takes both the input image and an importance map as inputs, and the importance map will get the compression quality spatially. Besides, to get a perceptual friendly image compression model, we apply perceptual loss and gain loss as parts of our optimization objective. Our backbone network is a variable rate version based on the work of Zhongyu Guo et al. In CLIC 2020. It can be divided into 4 parts: analysis module, quantizer, entropy model, and synthesis module. Specifically, an input image X is first transformed into latent representations Y through the nonlinear controllable analysis, which is conditioned on the map. Then the latent Y will be quantized and transmitted to the decoder side by arithmetic coding. After transmission, the discrete latent variables Y hat will be mapped to pixels X height, which is also conditioned on the decoding map. To formulate the distribution of Y hat for entropy coding, Gaussian mixture model is utilized in our codec, where the parameters of Gaussian mixed model are estimated through the hyperprior networks, which includes hyperanalysis and hypersynthesis, 3D context model, and residual parameter estimation module. The 3D context model, which leverages the dependencies along both spatial and channel dimensions in latent features, wherein a more accurate probability estimation model is achieved for entropy coding. Furthermore, we realize variable rate image compression with the aid of spatial feature transform layers, which takes an intermediate feature of previous layer and a prior condition to produce element-wise scaling and shifting parameters. This is motivated from the method proposed by Song et al. In ICCV 2021. In contrast to that work, we abandoned the spatial feature transform layers inserted into hyper transform networks to reduce parameters while still achieving comparable performance with models trained for specific bit rates. Concretely, we insert the special feature transform SFT layers into the autoencoder. The SFT layers takes a quality map as the input, enabling convolutional networks to be aware of the parameters of element-wise affine transformation. With the help of such conditional transform layers, the network achieves the property of controlling intermediate features within the encoding and the decoding transform networks, which helps us building an image compression model with controllable bit rates. At the decoder side, the map is decoded from latent Z hat, and therefore there is no extra transmission overhead. Besides, by using a controllable map, we can obtain the ability of bit allocation in spatial dimension to some extent, which can helpful when taking consideration of region of interest. The training losses of our final model include read loss, generator loss, and discriminator loss. The read loss R represents the estimated bit rates. The generator loss shown here is a weighted combination of MSE, multi-scale SIM, LPIPs, and GAN loss. The LPIPs loss calculates the feature distance of a deep neural network and encourages decoded image to preserve more textual details. A conditional GAN is also applied to improve the subjective quality of reconstructions further. The weight of MSE loss, lambda I, is a pixel-wise weight and determined by the spatially varied quality map, while the other weights, lambda I, lambda L, and lambda G, are scaled versions of the sum of MSE weight, lambda I. Then to achieve the capacity of variable spatial equality, we incorporate several patterns of random quality maps in training. The random maps are independent of image content and are shown at the bottom of the slide. From left to right, there are uniform maps, Gaussian mixture maps, gradation maps, and random block maps. To improve the subjective quality of decoded images, we use silencing map as the quality map for region adaptive quality control. Here is an example of the silencing map and decoded images. The silencing map is generated from a pre-trained silencing detection network, and the lighter region corresponds to higher quality. As you can see, when the background is blurred, the reconstructed image with silencing guided coding preserves more details in the foreground. That is a human face in this figure, while the reconstructed image without silencing guidance is so much more smoother. Silencing guided quality control provides better perceptual compression results at various image regions. The quantitative results on validation dataset is shown in this slide. Our method achieved the first place in valid phase at 0.075 BPP and 0.15 BPP in terms of multi-scale SIM, demonstrating that our method can perform well in both subjective and objective measurements. In conclusion, first, we develop a perceptual image compression model that supports variable rate coding and region adaptive quality control, while still delivering relatively good objective performance. Second, we currently use the silencing map of pre-trained networks to get region adaptive subjective quality optimization, which can be improved further in the future by designing more effective end-to-end optimized networks. This is the end of my presentation. Thank you for listening, and I hope you all enjoyed my talk. If any questions, please let me know. Thanks.
We probably have time for 1 or 2 questions if there's one in the room or in the Zoom call. Okay, great. Thank you so much for your talk. I think we have team PK USZ 201. I think I saw you in the call. More. Team PK USZ, are you ready to present? Okay, you should have the ability to present now. Hello, I think we can hear you, but we don't see the slides.
Can you see the slides?
Yep, we can see the slides and we can hear you now. Perfect.
Some problems. Oh, I start now. Hello, everyone. I'm Wei Jiang from Peking University. It's my pleasure to give a live talk here. I will introduce our model proposed for CLIC competition this year. First, people have different evaluation standards for different types of textures in images. For example, for grass texture area, if you shift it a few pixels to the right, the pixels are misaligned and its PSNR value will be decreased. but this change cannot be noticed by people. However, in the face area, even small distortions can seriously affect the perceptual quality. The previous compression models are optimized based on a globally unified distortion function, which will cause some problems. As shown in the figures, the model optimized for MS sim generates a vivid water surface, but the face reconstruction has unacceptable distortions. The model optimized for MSE is just the opposite. It has high accuracy on the face, but the generated water surface is too smooth. People have different evaluation standards for different types of textures in images. Here's an overview of our proposed model. In our model, the images are divided into two kinds of regions. The first kind of area includes human faces, texture, and so on. People require such textures to be accurately reconstructed. For the second kind of area, more attention will be paid on the perceptual quality, even if it deviates its original textures. Thus, a ROI-guided optimization model is introduced. Firstly, a weighted mask from silence map is used. Secondly, according to the differences of ROI and background area, different losses are applied separately. What's more, GAN and LPIPS are used to generate more texture in the background. In short, we use MSE for ROI regions and LPIPS and MSIM for backgrounds. At last, variable rate method is adopted to realize rate control, and it performs well with the perceptual metric. Now, I would like to talk about ROI settings. First, we get ROI maps from a silent object detection model. We use average pooling to resize the mask, since we need to multiply it with latence. We use a factor alpha here to change the weight of ROI regions. Here, a smaller alpha means more bits are allocated to the ROI latence. Another tips to be paid attention to is that the channel protection. Here, a certain number of channels are protected to retain appropriate information for the background to avoid the fading of its reconstructed texture. Assuming there are 192 channels in latence, the first 48 feature maps are protected, and the following channels are weighted. Another tip is that usually ROI masks are needed to be smoothed to avoid anti-effects. You can see in the red box here. If the mask is not smoothed, we will get some anti-effects. Thus, the latent ROI can get according to this. We also use FID, LPIPS, and MSIM to evaluate the performance of our model. Here is the performance of our model when it is evaluated by FID and LPIPS. Here is the performance of our model when it is evaluated by MSIM. Next, I will show the visual results comparison between our model and other advanced models. As shown in the figure, in the texture of the head in the first column, our model retains more accurate luma and chroma information. In the face area in the second column, our model generates more vivid and accurate texture. And in the text area of the third column, even if the reconstructed text of HiFi is no longer readable, our reconstructed text is still clear. In comparison with models optimized only for MSIM or MSE. Our model shows better perceptual qualities. As shown in the figure, our model has superior subjective quality, even if the bit rate is much lower. Now, here is the reconstructed image of our model. Thank you for your attention. If you are interested in our work, feel free to contact us.
Great, thank you very much for your presentation. We're running a little short on time, so we're gonna move on to newbie codec. If there's a representative in the Zoom chat.
Oh, yes. Can you hear me?
Yes, I can.
Okay. So please wait a moment, and I will share my screen.
Yes, just one moment here.
So the Zoom meeting room seems that I do not have the permission to share my screen. How can I do it? Can you help me?
You should have it just now if you retry.
Okay. Oh yeah, seems good. Okay, I think it works. And can you see my screen now?
Yeah, you should be good to go.
Okay, so let's get it started. Hi everyone, greeting from Beijing, China, and this is Dailan He from the team Newbie Codec. I'm studying from SysTime. I'm studying for the DSP and Codec group of SysTime research. And thanks for the invitation of the organizers. And this talk introduces our image coding solution for the 5th CLIC challenge. We will present how we design an efficient learned image compression model that achieves remarkable rate distortion performance while maintaining a reasonable running speed. And at first, this is an overview of our methods. There are 2 parts of the solution. The first is an end-to-end learned image coding model with joint prior. I believe most of us has been very familiar to this architecture. And the image is transformed to the latent features with a hyperprior model and a quantized model to estimate their distributions, so we can attribute coding them. And particularly, we use our newly proposed CLIC model as the backbone with a multi-dimensional quantized model called the assay context, which is marked in this region. And the CLIC paper has been accepted by CVPR 2022 as oral presentation, and it is the most essential part of our methods. So we will introduce it later. And the second part of our solution is the perceptual-oriented training with a combined loss, including the perceptual loss for RPS and the pixel-wise loss. Similarly, it is a R1 or R2 loss, yeah, and the GAN loss and the style loss. This part is similar to many other learning-based methods optimizing the human perception. So we will just, for simplification, we will just omit it and talking about how we make an efficient learned image model. Yeah, and just as mentioned by Mr. Lucas, our submitted neurocoder has the fastest decoding speed among all learning-based methods in the image track. This is encouraging. So we use the large model. We spend about only 500 seconds to decode the challenge datasets, which is significantly faster than the other teams. As now, the learning-based method is stepping into practice. We believe this faster decoding feature should be highlighted. So let's take a look at how CLIC saves the decoding time. As we know, most of the best LSA models adopt the quantized models for rate reduction. This technique models a factorized distribution, which leads to little entropy and bit rates. And the earliest proposed and most popular context model is this autoregressive model. It can will increase the RD performance, yet introduce an extremely slow serial decoding. This serial decoding makes many SOTA models like the Google ones and yes, the CLIC 2021 champion solutions. Yeah, and they make them very, lack of efficiency, and make them require more than 1 second, second to decode a high definition image, which has been thoroughly discussed by Mr. Vigas, and we appreciate his excellent and inspiring talk. To address the decoding speed issue, we proposed a checkboard model last year. It has been just shown in the center of the screen. By adopting a 2-path parallel decoding, the efficiency is significantly improved, and we will discuss it later. And another method is the channel-wise model. The channel-wise model is another alternative. This model, unlike the other 2 spatial context models, splits the features into many chunks along the channel dimension and refers to earlier decoded chunks as the context features of later ones. So we can see in this figure, the blue chunks are first decoded and the white ones are later decoded. So the blue ones can be used as the context feature of the white ones. Because we just split the features along the channel, so the granularity of the splitting can just be controlled by us, which means that we can split the chunks, split the features into fewer chunks than the HW, than the spatial features, number of spatial features, which is more efficient than the serial context model, but still less efficient than the two-path parallel spatial context models. And these 2 parallel context models are both powerful, and they are applied along different dimensions. So we assume them just orthogonal, and recommend to combining them. This is the background and the motivation of our ALEC model. In the ALEC paper, we propose a new context model, the IC context. It refers both intra-chunk and inter-chunk context information using 2 different context models, which means the spatial one for the intra-chunk context model, and the channel context model for the inter-chunk context modeling. Yeah. And let's have a look at how this algorithm works when decoding the images. Initially, because we don't have any context to work with, we infer the entropy coding parameters straight from the pre-stored hyperparameter features, which has been simplified by us, and decode half of the first chunk features from the bitstream, which is the red ones. The red ones is the half, the checkboard shaped half features of the first chunk, and then we see this half chunk as a special context, and we call them the anchors. And we can just input the anchors to the special context to compute the context representation for the remaining half of features. That means we can infer the other half of first chunk using the spatial context model. And this is the checkboard context model we just proposed in the last year. Yeah. And just now we just apply this spatial context model on the first channel chunk of the features. You can see that now we do not have the channel context model because we do not have any decoded features, and we can just use the spatial context model on the first chunk. This is what's the mean of intra-chunk model. Yeah. And after that, we'll decode the second chunk using the first as channel context. We feed the first chunk into the context model, and decode the anchors of the second chunk. This is just similar to the first chunk, but the first chunk is used as the channel context. This is the only difference. Yeah. And then we can decode the other half with both the first chunk and the anchors as context. As a result, the second chunk is decoded using both spatial and channel context model. And then we decode the next chunk with the obtained 2 as channel context. And repeat the loop till the end of decoding of all chunks. This chunk by chunk decoding costs a lot, as we usually use a K or more than 10 channels to ensure the RD performance. Therefore, we further investigate on an unevenly grouped channel-wise model to speed up it. Yeah. And this is motivated by our observation of unbalanced information distribution among LLC features. We call it the information compaction property of LLC. When using a channel-wise context model, the most important channels with stronger activations are more likely to appear in the earlier decoded channels. You can see this figure, the 320 channels are grouped to 10 chunks, and we just decode the chunks one by one. And the information will just compact to the earlier decoded chunks. This is an observation, and we just simplify it. We just simplify the presentation of these slides. If you are interested in it, you can refer to our original paper for solely analysis of this property. Yeah, and yet most of the other channels contains much less information. I mean the later channels contains much less information. Contributes less to the contextual modeling. It inspires us to adjust the grouping scheme, and different from the existing 10 slice grouping scheme, we just propose to unevenly group the channels to less chunks. We slice the later decoded chunks coarser, and that means we can save the calculation volume. Yeah, and now we have the 4 grouped. The five grouped unevenly grouping scheme, and which can save the calculation. This promotion can speed up the essay context and achieves comparable RD performance. You can see that when we adopt the channel-wise context model with the spatial context model jointly, it can even outperform the evenly grouped spatial context model. And yes, with a slightly improvement. And the most important thing is we can significantly save the running time of this context model by introducing this unevenly grouped methods. And so we implant the essay context into the LLC model and obtain the ALIC model. To further balance performance and inference speed, we simplify the transfer network by replacing GDN layers with more general used REST blocks. This makes ALIC scalable, and so we can just configure the dips of the transform network to easily control the capability of the model to obtain a better reconstruction quality. And finally, we present the figure to show how ALIC balances the performance and the speed. It achieves a better RD performance, where it can real-time decode high-definition images. We believe the proposed methods can further improve the LLC study to make it more practical and valuable. Now we have proof that ALIC performs well on objective metrics like PSNR or MSIM. With the efficient and powerful ALIC backbone, we simply introduce the perceptual optimization to improve our CLIC submission. Note that since we solved the decoding speed issue, we can use a larger model without exceed the decoding time limitation to achieve a better reconstruction quality. I think this is the most important reason of why we can achieve both better decoding speed and perceptual quality. And this is the end of our report. Thanks for your listening. If you are interested in our CLIC paper, welcome to visit our poster session for further discussion. And now it's my pleasure to answer your questions.
Thank you for that presentation. We might have time for one or so questions here. If there's anybody on the Zoom or in person. Looks like George has one from the Zoom. Where's most of the time spent in your model? Is it the transforms or the entropy-related subsystem?
Okay, it is a good question, and thanks to Dorothy. Okay, from now on, okay, I think in these two configuration of CLIC, and the most costful part is the transform networks, and if you use a shallower network of the of this nonlinear transform network, you can just balance this cost from the major network to the context models. I think this is one of the advantagements of our model, which leaves you room to configure your model and to make a trade-off between the two parts of the model, just for different purpose. And we are just looking for a new architecture and to further to better balance this trade-off between the two parts. And how about encoding latency? Okay, I think the encoding latency is just similar to the decoding latency, because our context model, as you see, you need the same encoding scheme just as the decoding scheme to do this channel-wise and spatial-wise context modeling. So the encoding algorithm is just very similar to the decoding algorithm. I think the most difference is the latency of entropy decoder and entropy encoder. But it is out of the network. It is out of the network inference. So this is more close to an engineering issue. Yes.
Okay, again, thank you for the questions and thank you for your talk. We're gonna take a break for about an hour. So we're gonna be back here at 1:25 or 13:25 local time. Okay, everybody, welcome back. We're going to be starting the afternoon session now. Our first talk of the afternoon is going to be Saki Weisman. I believe you're in the Zoom. Let me give you permission to present.
Yes, I am. Thank you. First, can you see me? Can anybody see or hear me?
I'm not sure we're getting video. That might just be, or audio. That just might be on our end.
Okay, so but you do hear me. That's a good start. And maybe it's fine if you don't see me on video. I'll just share my slides. I mean, so should I share the screen?
Can you give me an audio check?
Checking 1, 2, 3.
Perfect. We're getting you here crystal clear here.
Okay, now video.
I think you have, yep.
Yeah, go ahead.
I think you have permission to present. So.
Okay, so that means I need to share my screen, or?
Yes, if you can share your screen and then just go through your presentation like normal, you can do it at your pace.
Okay, so let's see. Wait, I think this. Oops, wait. Cool. So, can you see my slides?
Yep, we can see everything. You are good to go. Thank you.
Wait, and can you see me?
Yep, we can see you off to the side,
okay.
but mostly the slides. Yeah.
Okay, but so okay, maybe you okay, you'll have to suffer seeing me, but hopefully very small. So hi everybody, it's a pleasure to be here. Many thanks for the invitation, and I truly regret I can't be with you or with some of you in person. But in any case, I'm Saki Weisman. I'm from Stanford EE, though I'm currently largely on leave at some industrial place, which if I put on the slide, I'd have to go through this whole process of showing them the slides and getting vetted and so on. So I won't mention it here, but happy to talk offline. So the title I gave for the talk is on text-based image and video compression. And the point, oops, why is this not, there we go. Okay, so I guess the main point I'm going to try to get across is that text and language, and I'm going to use that sort of interchangeably, maybe with nuanced differences in the meanings, which I'm going to leave to your intelligence to infer. We're going to see this manifested in this talk as a corpus for compression and as a tool for assessing the potential for improved compression over our current technologies. We're going to see and use this as a code for doing actual compression, also as sometimes the core content in certain multimedia scenarios that we should focus on. And finally, and this is more sort of slightly more futuristic, but not sci-fi, is as a driving vehicle potentially for realizing what I think would be dramatic compression gains in our current and emerging multimedia modalities. So let me start with a work that was published, submitted in 1950, published in 1951 by Shannon about sort of what he called prediction entropy of printed English. And what he basically did was use a human, one human, his wife at the time, to ask her to predict the next letter of an English text. And according to her sort of performance, he was able to kind of transform her prediction error to what today we would probably refer to as prediction loss under log loss, and through that get an estimate of the entropy of the English language. And as the estimate that he got was about 1.3 bits per letter. And in fact, more recently, like late 70s, my late colleague, Tom Cover and his student essentially repeated that experiment. The details vary, but essentially repeated a very similar experiment, this time with 12 people. And they got a very consistent estimate of about 1.3 bits per symbol for the entropy of English text. And very recently, I think this as recently as this year, essentially, we had a group that redid the experiment, this time with going on Mechanical Turk using 683 humans, and got sort of a very similar estimate of about 1.22 bits per letter. But the main point I want to get across, or to sort of to note here, which is largely inspiring for us in what I'll soon tell you about, is that, you know, as early as the early 1950s, you had Shannon, who was able to use humans and, you know, their ability, their sort of internal models in their heads, in their biological neural nets that they had, to show what should be achievable, right? He used humans to basically give an estimate or even an upper bound on the entropy of English text, which should be achievable for compression, right? So that was with humans as early as the 1950s, but it's only fairly recently, in recent decades, that our technologies have started to catch up. And I would argue that only as recently as, you know, the last couple of years, we had actual compressors that have realized, that have sort of delivered on what Shannon showed through humans should be achievable. And so with this sort of inspiration in mind, our goal for sort of lossy multimedia compression has been in this sort of line of work that I'll describe to you now, to understand from humans, also through humans, what might be achievable once our algorithmic models, our algorithms, catch up to those in our brains, once potentially our code books and coding, decoding, however we want to think about it, make good use of humanity's publicly available site information. And once we effectively also tailor, this is something that we didn't have in the context of lossless, but in the context of lossy, of course, extremely key is to effectively tailor the reconstructions to what humans actually care about. So the initial experiment in this direction was done actually with three inspiring high schoolers, Ashu, Sean, and Soham. And basically what it boiled down to is one high schooler getting a photo they've never previously seen and not to be found on the internet, and charged with describing that photo via text to another high schooler who just needs to, on the basis of, you know, reading the text descriptions, to come up with their reconstruction of the image. Okay, so that's essentially the experiment, and what we did was evaluate sort of this human compressor. So, you know, you've got a human encoder, a human decoder, if you will, and then there's the compressor presentation, which is the size in bytes of the compressor presentation of the text. So we went out and compared that to, ostensibly our best current lossy image compressor, WebP. And so we basically, looked at how well WebP would compress if forced to a similar size of the compressed representation. And the quality of evaluation was not mean square error, but comparing under the quality of the reconstruction as would be assessed by humans. And we went to Mechanical Turk and asked, for every sort of pair of images, we asked 100 humans to basically to give us a score between 1 to 10 for their level of satisfaction. We would show them, okay, here's the original image, here's the reconstructed image, how satisfied would you be on a level between 1 and 10? So no, this is not quite, we're not asking exactly how similar or how loyal is the reconstruction to the origin. It's just like you have a human, how satisfied would you be if that were your reconstruction? And so here's some examples. So the idea was, as I said, so you had the original image, then you had the human compressed image. So as you might imagine, this was typically like the humans, it took them like typically for one image, like a full day of writing text descriptions to the other human. But as you might imagine, it boiled down to order of, the overall size of the transcript of the text was in the order of kilobytes, or is this kilobits? I think maybe this is kilobits, sorry. So, but as you might imagine, we're talking about extreme compression modes, like 3 orders of magnitude compression. And then, what we would compare is to like WebP forced to operate at a very similar compression rate, and we always want to be more righteous than the Pope. We always went for WebP at a working point slightly higher in terms of rate than what the humans did. And so you can see, like in this case, the human reconstruction got an average satisfaction of 6.28 versus the WebP, which was less. So here are a couple of additional examples. You can look at this one here. I would argue, so here too, the human compressor, got higher satisfaction. I would argue they could have gotten way higher satisfaction if they got the number here correct. So the original number was 118, and they had it 160. Here's another example. This one is interesting in that it involved the human identifying that the human was a local, and they identified that the photo was taken on California Avenue, one of our main streets in Palo Alto, and basically and so they basically used you kind of relied on a link to Google Maps of that photo of that intersection from the right angle, and they riffed on it. Here's another example. So here too, you can see that higher level of satisfaction by the human reconstruction, which is much sort of crisper and more loyal to sort of the fabric and, potentially kind of morally very similar bonfire, but less loyal to the details as the WebP is, but at the expense of being much more fuzzy. But just so you don't think everything was always rosy and the human compressors were always superior, here's an example of what the humans did with a human face. So in this case, as you might imagine, and you can probably agree, the WebP got much higher satisfaction than the human reconstructors that reconstructed a face which is not identifiable as the original person. Okay. So so overall they worked on 13 images, but for many of them they actually did much better than the existing technology than WebP for some of them, such as those that involved faces. It didn't do as well. But I think the main takeaway for us from that work was that there's substantial room for improvement over existing approaches to image compression, and that in fact human language can be an actual tool not only for assessing and discovering that there is potential, but also for actually doing also for realizing on this potential. So that piece of work we ended up writing up with those high schoolers and got some press, and it was fun, and we set up a website, and we called this sort of kind of research thrust hack, humans as awesome compressors. So now let me tell you a little bit about some related work, which we actually pursued because it was so fun with working with these high schoolers on so many levels. They also keep you young and they keep you modest because they show you all sorts of things that you never thought that can be done, and they actually do it. So we ended up sort of launching this STEM program for high school, for high schoolers, and for summer internships. The H in STEM standing for the humanities and the human element, that should always be either implicitly or explicitly incorporated into any STEM project. And this has been steadily growing number, and we've been able to reach now actually since COVID hit, also people beyond the Bay Area, and it's been really gratifying to work with many of these extremely inspiring students. And so I'll tell you about some of the projects with them that pertain to, I mean, there are many projects, but I'll tell you about a couple that pertain to our current discussion. So one was, to try and improve or, ask, okay, can we, so, in the context of facial images, we saw that the original experiment, humans didn't do as well. But the question still remained, but can you in principle also, with a handful of kilobytes or kilobits, actually do a decent job at compressing a face? And what we did was, for inspiration, work with a police sketch artist in the Stanford Police Department. And what I'm showing you here is an example of like one of the high school interns basically answering a sequence of questions. This was all done by email, and the police sketch artist basically asked her a sequence of questions, many of which were sort of multiple choice-based, others were slightly more open-ended. But basically the only thing that the police sketch artist got from which they came up with this reconstruction that you see here was just text that she sent in the email, and that text was just sort of overall 7 kilobytes worth of text. And based on that, the police sketch artist came up with this reconstruction. Now for kind of privacy reasons, I'm not showing her. This turned out to be her description of her dad. And if you saw the photo, the real photo of her dad, you would confess that this is really a good reconstruction and identifiable as her dad. So, and so this suggests that we could potentially also have compressors for facial images by looking very closely at, let's say, the work of a police sketch artist. But while we're getting slightly kind of provocative, I'll be even more, right? I mean, whether we like it or not, we're approaching a regime where all of us are going to be on some database and potentially, publicly available. So, we shouldn't need more than log the number of people on this planet bits to tell you basically, who the person is. And then, you're just going to retrieve that face, that photo of the face, and then maybe additional handful of bits to say, where the person's looking and about their emotions and disposition and so on. So here too, for sure, much potential for compression over our current technologies. Another thing that we did with another group of these high schoolers was to, revisit the original experiment and basically eliminate the human at the receiving end. And instead of the human, have a computer that generates the image. So basically what you have is still a human that looks at the image, and instead of describing text to another human, writes code. Code that is then deciphered by a computer to come up with a reconstruction. And what this did, in fact, simultaneously was both give us actually a better, so, for all these examples that I've shown you, they typically got like another order of magnitude reduction in the size, because when you write code for a computer, you write it way more succinctly. And also, this took care of all these issues with, reproducibility and so on. Now it's not a human that needs to read the text, it's a computer, and it's always going to be consistently the same reproduction. So now let me tell you about something that we did on video. So, think about like a typical Zoom session, such as this, right? The one we're having now, and maybe some of you are seeing me on the screen. But what really are you seeing, right? I mean, the background is static, and then me. Probably the first few seconds of this talk, you sort of got a sense of, definitely what I look like, and also how I speak, my voice, and the ways in which I tend to move my hands when I try to express things, and basically how this correlates with what I'm saying. All these things you've learned very, very sort of in the first few seconds of this talk. And then the rest, probably the only thing you care about is, and the only truly novel information, although if you ask my kids, even that's not particularly novel or exciting, is the text of what I'm saying, okay? So in principle, then, at least information theoretically, we shouldn't need more than a couple dozen bits per second to convey the text of what the human here is saying. And so with this in mind, with this sort of with this mindset, we actually kind of created a platform for that we called, this was like published in a paper, text to vid, ultra low bitrate compression of talking head videos via text. And the idea was simply to take existing, this was not about really the algorithms, but it was more about the idea that taking existing off the shelf stuff to to see what we can get away with if essentially all that we stream is the text of what the person is saying. So let me show you 2 videos.
Banding artifacts are artificially introduced contours arising from the quantization of a smooth region in a video.
Okay, that's the first video. And here's.
Hello, I'm going to talk about banding artifacts. Banding artifacts are artificially introduced contours arising from the quantization of a smooth region in a video.
Okay, so now if this were in person, I could see the room. Maybe I should be able to, but I can't. I would ask for a show of hands, like, okay, how many preferred the first video? And how many of you preferred the second? And probably, potentially, this would have been more or less like a split room, 50-50. But what turns out is that like the first video was based on this sort of idea that I described, and it required 100 bits per second. And the second video is just sort of, what our current sort of standards would need, and to reproduce, what you've seen. And it's like 3 orders of magnitude. It's exactly 3 orders of magnitude higher in terms of bits per second. And so you know, this part of in that work, we also did a subjective study, 240 participants. So I believe that this pair of points that I've shown you, I think they correspond, I think maybe to this point. So what does this point here mean? It means that we had like 50% of the people preferred the reconstruction under this text to vid framework over, the sort of standard technology. And the rate that we needed, the bandwidth or the number of bits per second that we needed was, this is 1,000. So this would be like order of like 1,300, a factor of 1,300 less bits per second is the point. So, okay, so some of the next steps and challenges, I think we're going to end early because I'm very happy to, and I'm hoping to, have some discussion. But some of the next steps and challenges are further development and automation of text-based image compression. And by the way, these are challenges largely for you guys, because I'm largely an information theorist. I just talk about what should be achievable. And but I think that what I've shown you strongly suggests that we should be doing way better, let's say in the context of image compression, and that we could be doing way better if we work with text-based image compression. And there are already frameworks out there that are emerging that could be like baby steps in this direction. Many of you know this framework DALI for creating images for text. And there's work by my colleague Fei Li et al. About extracting basically text descriptions from images. But obviously this is way more primitive than the ways in which humans can do it. So I think lots of room for improving on this front. As far as the text to vid framework goes, obviously work in improving sort of both sort of the quality of what we've been working with, which is some clunky off-the-shelf stuff, and also obviously in terms of complexity. I mean, this is currently way too complex to work on like a simple handheld phone. But fundamentally, there's no reason why you couldn't implement this at very low complexity. Use text as sign information for other elements. So, think about the potential for, okay, you stream text, but now you want to do something. Now you want to add some layers of nuance that pertain to the video. Maybe that pertain to the audio and elements of the actual video, but use this text non-trivially as sign information for enhancing these other forms of data that you may want to reconstruct. Also harness the predictability of text. I mean, text is so predictable, as I said. Many of you know. I mean, today your Gmail predicts you better even than you can what you want to say, and my kids will tell you that they can compress any sentence or even whole paragraph that I want to say into 1 bit after I utter the first syllable. So this is a lot of potential, not only for extreme modes of compression, but also in fact for having real-time reconstructions, right? I mean, if the decoder can do sort of predicting reconstruction based on the text, then you could have like real-time, faster than speed of light reproduction. And also another sort of thing that kind of is currently slightly tongue-in-cheek, but no reason why it shouldn't be a reality, is streaming scripts, right? So think about Netflix having to only stream like the script of the movie, and then the reconstruction can be, in fact, can be user-based, can be like reconstruct a movie with this script, the actors being, the favorite actors of the person watching, and potentially also, and even more concretely, there's, you can think about streaming from human text, like a script, to machine code, which would be like a script to a Unity engine that can actually, sort of implement the movie without any real actors or anything, like a true, and basically form a very effective decoder. And then finally, I'll leave you with the thought that whatever you can do here, let's say in the context of video, you should be able to do, and with even more dramatic savings and results in the context of all these emerging new modalities, right? VR, point clouds, and so on. The text, using text can be a source for both sort of, again, forcing you to distill and squeeze out of the information what the human would actually care about, and then also, stream it with like 3 to 5 or whatever orders of magnitude reduction in the bandwidth needed. So with all these points, okay, yeah. So I guess just to recap, I guess my key takeaways, much potential for improvements over our existing technologies for multimedia compression and streaming, and the fact that we know that there is much potential is largely thanks to human language. And as I tried to convey with the work that I described, it's both a powerful tool for assessing what should be achievable in principle, and potentially also the vehicle for delivering on it. Okay, so I'm going to leave you. Okay, I'll share the slide so you can look at the references that cover the work that I mentioned, and some related references. And I'm going to leave you with this slide of acknowledgements and inspiration. And I hope that I left some time for questions. So please bring it on, and be as aggressive as you feel that I deserve, and even more. So maybe I'll, thank you.
So yeah, we have time for a couple of questions if there's any in the Zoom or in the room.
I would love to be able to see the people, or some of the people, or at least someone who asks a question.
I could turn my laptop around, but it's going to make a lot of noise. So we might just have to do audio. Yes, we got somebody in the room.
Thanks. Super interesting talk. I'm very curious how you see beyond building a database of all human faces, and how do you see this whole fidelity question?
Actually, I so apologize. I almost managed to understand. Can you speak up just a little?
You can just come up here if you want.
Sure. Better? Probably. Thanks. Super interesting talk. I'm wondering how you see this whole fidelity question for especially video compression. I mean, for this use case you showed, it makes a lot of sense to just have the text and you can probably generate a lot. But for more general videos, how do you see this beyond, like you said, building a database of all human faces and basing it on that? Thanks.
I mean, I don't have probably a satisfactory answer, and this is largely what I'm leaving to the community to figure out. I think it will involve working much more closely with potentially with psychologists and people we are less used to interacting with. There's also, I should have maybe given a more explicit shout out. There's a framework that we've now sort of given that we now opened up some platform that allows, in the context of video compression, human input into what humans actually care about at any given point in time and space. And we're trying to collect, so we're trying to kind of crowdsource and collect a lot of data from which you couldn't envision doing kind of machine learning to sort of infer implicitly and explicitly the more relevant distortion criteria. And yeah, and I feel like, yeah, so it will involve lots of further work and interaction and observations of humans. Let's say in the context of VR, you're going to have to work with humans and look at them very, very closely and collect much, like orders of magnitude more data than is currently at our disposal to to try and glean sort of actionable insights about the right sort of distortion metrics. And again, I apologize, this was a very short, long-winded way of saying, I don't know, right back at you.
So we had a couple more questions from the Zoom. Abhishek asked, how does text-based video compression handle motion information if the background is rapidly changing? Isn't motion consistency a challenge in text-to-video compression?
Right. So I should say, well, I should say a couple of things. One, I'm sort of the information theory oriented advisor who gets to just sit and talk about vague ideas, and then I have the highly capable students. In this case, our PhD student Paul Kitt, who goes off and tries and actually implements very capably these ideas in practice. So probably less the person to comment on this. And so also from my kind of viewpoint, the main contribution also of this text to vid, at least this initial paper, is not so much about the technology as it is about sort of information theoretically prodding the community to say, hey, look, we should, look, what we're showing is that with a handful, with a couple dozen bits per second, right, you can achieve reconstructions that 50% of the population will prefer over reconstructions with our current technologies that require like 1,000-fold more bandwidth. So that's the main contribution, and then exactly how to go about achieving it. So what I currently showed was with these sort of very clunky, publicly and freely available off the shelf technologies, but there's no doubt that people like you guys in the audience should be in position to implement these things way more exquisitely and also practically computationally. So again, very long winding answer to your question, saying basically, I don't exactly know how you would do it like in practice and how you would get kind of more nuanced reconstructions that go beyond just the text of what the person is saying. But all these things I'm mainly sort of opening up to the community to consider.
We have a couple more in the room if you want to take those next.
Yeah, absolutely.
And
I would love to be able to see something.
So, hello.
Oh, yes.
So, great talk.
Thank you.
So, I have a question. I like modern art, and I was wondering how you could expect to describe properly with this kind of approach a piece of art at the MoMA or somewhere. And more generally, what do you think of the signal which we have difficulties to capture with text? How we would measure from an information theory perspective what you're missing, where you're restricting the description and the reconstruction to what you can describe by text. Do you have some thoughts about that?
So thank you for the question. And yet again, but this time maybe I'll start with the short answer and maybe even end there. Is that I don't know. I think it's a great question, and I don't have anything particularly wise to share with regard to how to address it. Like, you know, in sense, okay, like, you know, what really truly, first, even information theoretically remains over and beyond the text once you've conveyed it. I think it's a great question. Again, would involve probably brainstorming also with, you know, psychologists and you know, psychoanalysts. There are probably some interesting experiments that could be, you know, that one could think of. But again, I haven't dedicated enough time, or maybe I'm just sort of, I'm not inspired enough, because I did try to think in that direction, but I don't have anything currently, like a concrete suggestion for how you would go about measuring these things. But I feel like there are some really interesting experiments lurking out there to be done and to shed insight.
Okay, thank you.
Hi, thank you for the provocative talk, and I like the idea of if we can do anything to decode, what should we transmit? Yeah, but I wanted to ask about when we observe anything, we always have a task in mind. So reconstruction is a good proxy when we don't really know what we're going for. But have you given any thought to that aspect?
So again, the short answer is I don't have anything satisfactory to say. And again, I think it will have to, and I did mention, like in the context of video, where sort of we've created a platform for people to sort of give us feedback on, or you know, to provide sort of data points that I think could be used for gleaning insight into the relevant and quantifiably and, you know, quantitative forms of much more relevant sort of distortion criteria. But no, I think, and I agree, and I'll just repeat what I said before, which is I think there's room for a lot more work with humans, observing humans, and also getting probably other types of human specialists into the loop to get a really, you know, much more concrete, quantifiable, and actionable understanding of the relevant sort of notions that we should be optimizing for in the reconstruction.
Yeah, thank you. I was just thinking that, yeah, maybe we should even be measuring like brain activation.
Oh,
like,
interesting, interesting. So now you're saying forget psychologists, bring in neuroscientists, and just look at the level, just look directly at the level of excitation of the neurons.
Yeah.
As your proxy for the goodness of the reconstruction. Yeah, yeah.
Anyway,
agreed.
Thank you.
Thank you.
We also had one question from George over Zoom. He was talking about Dolly imaging can create absolutely stunning images out of text. At what bit rates does it make sense to use a semantic text versus a signal processing representation?
Yeah, that's another good question. I don't know. I think it involves more work and experimentation. Currently, obviously, you know, the technology is such that we can only sort of look at very different orders of magnitude, right? I mean, with the text-based descriptions, like it's in the order of, you know, sentences or paragraphs. And if you put humans in the loop, it's in the order of like what a human can write maybe in a day, versus, you know, the current modalities that are based on, you know, the sort of standard image processing is a few orders of magnitude higher in bit rate. I would argue that potentially, I think there's a lot of potential to work with text, and again, not even thinking necessarily text like that a human writes, but just as building on the initial very extreme compression points, but building on that to go to higher rates, using sort of machine, human language as a code, even though it's not really to be uttered by and understood by a human, but to use, all our existing technologies for using that text as a code. I think there's potential for improving on, even on working points that are currently kind of orders of magnitude beyond what we're doing with text currently.
And I think we have 2 more in-person speakers, but then I'm gonna have to cut it off so we don't go too far over. So if you want to come on up.
So, happy to take it offline if we're.
Hey, yeah, thank you again.
Oh yeah,
very nice.
My pleasure. Thanks everyone. Bye.
Oh, I had a question actually. I think we have time for 2 questions, right?
Okay, but I think I was told we're out of time, so.
Oh no, we have time for 2 more.
I'll happily take this offline. Oh, okay. So, okay, so let's go quickly.
Okay, yeah, so thanks. I like that you're focusing on these extremely low bit rates. So this of course means that you have to generate a lot of the stuff, right? And you showed that in your talk. And I think that you also, from your examples, it shows that in order to do so well, it works best if you rely on like a large library of maybe images or knowledge. So in the end, you're increasing decoder complexity. And we saw this morning that other people care about decreasing decoder complexity. So do you think these 2 are fundamentally at odds, or can they be reconciled, these 2 goals?
My short answer is that I'm not aware of any theoretical work. I mean, in practice, in terms of our current technologies and thinking, there always seems to be some sort of a tension between, compression, how small the file can be, and the complexity at large, and then within complexity, encoder versus decoder. It always seems to be like a zero-sum game. But I want to challenge everyone to think outside of this box. I really don't know of any result, any fundamental result in information theory or complexity theory or anything that that suggests that we can achieve everything that we've currently seen is achievable sort of information theoretically with very low complexity, implementable encoding, decoding, and so on.
Okay. Okay, yeah, thank you very much.
My pleasure.
Hi there. Great. Thanks for a great talk. So I mean, just the compression ratios that of human compressors, you're describing them as to be in the order of thousands to what we currently have, and I mean it's on one side it's very impressive, and on the other side it's kind of embarrassing and puts the compression that we have right now to shame. And so I guess
although my point is not to embarrass, but more to provoke and to encourage thinking outside of the box of the current technologies.
Of course, yeah. I guess it's just my question sort of is, what do you think is there any component that is missing from the way that we currently do traditional compression that you would like to? So you're provoking, but are you also suggesting some sort of like what should we think of as improvements to us? Is it just bigger model sizes? Do we just need to cram in more human biases in our models?
Right. I feel like maybe, again, I don't know, but I feel like way more proactivity in working closely with humans, both sort of observing humans, having them in the loop as we design and think about our algorithms, and also potentially branching out to new types of human specialists from areas that we're not used to kind of collaborating with when we do video compression.
Okay, cool. Thanks so much.
Thank you.
Thank you so much for your talk. One more round of applause.
Thanks a lot, everybody. It's a pleasure. Thank you so much.
We're going to move on to the video track talks. For the fourth place team, Night Watch, I believe I have a video to play for them. So let's see how well this works over Zoom.
Computation. We are here to introduce the solution we proposed in the CLIC 2022 computation. Our title is Hybrid Video Coding Scheme based on VVC and Spatial Temporal Attention Convolution Neural Network. In the CLIC 2022 video compression task, the organizers provide 30 videos. Each video is 10 seconds. We need to encode each video at 0.1 Mbps and 1 Mbps. Each video comes from a different sensor. So we take a total video quality as our optimization goal, because the total size is fixed. Therefore, we need to assign the appropriate bit rate for each video, so as to obtain the highest overall encoding quality. We use a dynamic rate control strategy to complete the allocation of coding rate. The specific method can be obtained from our paper. Next, we proposed a simple multi-frame fusion model to further improve the quality of this reconstructed video. Then we introduce our experiment results. We present our experiment results here, where our method achieves good ranking in the validation set. Thanks.
So unfortunately, they won't be able to take questions, but maybe a round of applause for their presentation. Thank you. And we should have team ZXCRD 2022.
Hello?
Hello?
Hello? I can't share my screen.
Oh, yes, just give me 1 second. I need to give you permission. More. Okay, you should now have permission to share.
Hello, everyone. I'm Wang Yonghua from ZTE Corporation. Today, I'm going to talk about the neural network based in loop filter for CLIC 20 and 22. Introduction. The video compression CLIC challenge goal is human writing task. The goal is compress a corpus of videos.
Just 1 second. The audio is coming in a little quiet.
Okay. Can you hear me?
That sounds much better. Yes.
Okay.
Thank you.
Okay. The validation is 30 sequence of 10 seconds, includes lossless, webcam, and general videos. The evaluated metrics is PSNR for leaderboard score and subjective score for price. Our method includes 3 aspects. First, find the video codec baseline. Second, the optimization of traditional encoding, QP adaptive adjustment of iframe, the distortion optimization based on SSIM. Third, adaptive in-loop filter based on CNN. First, we find the video codec baseline. We choose VTM 15.0 as the encoded baseline. Our encoding configuration is the RA configuration, and the perceptual quantization encoding is used. The QP adaptive adjustment of iframe. This is the method for static and slowly changing sequence. Step 1, we determine the QP offset of the iframe based on RC method. Step 2, we set the optimizer QP for the perceptual quantization encoding of the iframe. Just like the figure 1, the green column, the QP offset is -3. As shown in the blue column, the QP offset is determined by the RC method. The vector distortion optimization based on SSIM. We know that the current RDO criteria in the VTM MSE used as a measurement standard, and SSM is, but SSM is more in line with human visual perception system. So we do the conversation between the SSM and the MSE. Finally, get the final function. Third, the adaptive in-loop filter based on CNN. Here is the codec framework. The position of CNRF is in the in-loop filter. Okay. Now is the CNRF architecture. The input is a reconstructed image, predicted image, boundary strength, and the quantization parameter. After the convolutional layers, here we use the attention residual block, including channel attention block and spatial attention block. After our CNRF, the input image quality can be improved. Our CNRF architecture is conditioned on different QP, leading to a unified model to handle different quality levels. Okay, our training process, we're converting the dataset images to YUV 420 format. Use VTM 15.0 configured with RA for encoding and decoding. The optimization for training is use MSE to improve the convergence and stability, and then switch to SSM metric at 80% of the total training steps. For 0.1 Mbps QP point used 32, 37, 43, 48. For 1 million BPS QP include 22, 27, 32, 37. Okay, our implementation, the deblocking filter and sample adaptive offset is disabled, while ARF is placed after the proposed CNRF. During the process of CNRF, where to apply the proposed filter is based on RDO. The CNN on-off flag is also in the encoder parameter index. Okay, let's we can see the result, the performance at 0.1 Mbps, the first stream of one typical sequence. Left is VTM 50.0. The right is add with the CNRF. Another typical sequence. Left is VTM 50.0. The right is traditional optimization and CNRF. The results performance in the validation set. We can see that our method has a higher PSNR and subjective performance. Okay, we can get some conclusion. We propose the traditional method that just the QP of iframe and that distortion optimization method based on SSM. We proposed a CNRF. Finally, our method is not only a suitable amount of data, but also has a better objective and subjective performance. Okay, that's all. Thank you.
Great, let's give a round of applause. We should have time for one or two questions if we have one either in Zoom or in person. We're gonna have one question in person. Can you hear okay?
When training your in-loop filter, what was your ground truth you used?
The question one, what was the ground truth for the in-loop filter?
Okay, the ground truth is the original picture. Okay.
Okay, thank you.
Is the original picture.
Great. Let's do one more round of applause. Thank you.
Okay.
And we're going to move to Team Neutron Star.
Hi, I'm here.
Hello?
Hello. Hi, I'm here. Sorry, I didn't have the access to share my screen.
Yes, I'm trying to find you in the speaker list. Are you Kai or under a different name?
I'm Junru. Yeah.
Oh, thank you. Okay. Okay, you should have permission to share now.
Okay, I'm trying. Okay, it's okay. 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 Can you see me? Can you see me? See my slides? Yeah.
Yep, we can see the slides and you.
Okay. Okay. Thank you. Let's start. And hello, everyone. I'm Li Junru from ByteDance, and it's my great honor to have a chance to present this work in CLIC 2022. And the title is Neutral Star, a neural network enhanced video coding framework beyond VVC. And this is the outline of the presentation. First, I will introduce the framework of the purpose method. Secondly, I will introduce the purpose coding tools. And then experimental results will be shown. Last is the conclusion of this paper. In this paper, we propose a learning-based framework on top of the VVC standard. The software version is the enhanced compression model ECM 3.1, and ECM 3 is still under development. Based on the traditional structure, we involve more enhanced coding tools, such as block partitioning, prediction tools. Besides, learning-based in-loop filter and super resolution are also involved in the framework. At first, I will introduce the traditional coding tools and begin with the partitioning method. Code unit partitioning has been a long-standing problem in a block-based hybrid video coding standard, which determines the shape and scales of the basic code unit. Flexible partitioning framework plays critical roles in depicting the diverse local contents. In VVC, a quad tree, binary tree, plus ternary tree partitioning structure is employed. In this paper, we introduce a symmetric quaternary tree partitioning structure aimed at improving the coding efficiency for larger blocks. There are 4 types of UQT partitioning structures. According to the location of the largest subblock, the splitting shape of the UQT could be noted as left, right, top, and bottom. Unlike the QT, UQT divides a block into 4 paths and allow one certain direction. Compared with the QT and the multi-type tree, smallest subblocks generated by UQT could achieve deeper depths with once splitting and capture the rich details more effectively. Moreover, the UQT produced a new partition pattern which could not be achieved by QT or MTT with identical splitting times. It's worth mentioning that the dimension of the subblocks are limited in the power of 2, such that it is not necessary to involve new transform calls. And next, I will introduce the history-based affine model inheritance. A motion model could capture complex motion, such as rotation and zooming. The left picture shows an example of 4-parameter affine model with 2 control points. Affine model utilizes 2 motion vectors to derive the model parameters. As shown in the right figure, the motion vectors, also known as the control points, are derived from the neighboring coded blocks. It's a new feature in the latest VVC standard. In order to derive the affine model parameters more efficiently, we built a history-based parameter table to store the affine model parameters. The 4 parameters are inherited from previous coded blocks, even if the block is far away from the current block. With a affine model inheritance method, the coding efficiency could be improved. Next, I will introduce the learning-based coding tools. First is the CNN-based in-loop filter. In hybrid video coding standards, in-loop filters are adopted for removing the coding artifacts, such as deblocking filter, sample adaptive offset, and the adaptive loop filter. We propose a CNN-based in-loop filter, which takes full advantage of the compressed domain information and higher knowledge, including the reconstruction map and the prediction map and the boundary strings, and also the partitioning map. The compressed information could help the network understand what happened in the compression process. The network structure for interframe is shown in those two pictures. Value blocks are adopted as the main structure. Prediction signal and boundary strings are generated during the compression process, and also with the quantization parameters, they together are employed as the side information of the network. For the chroma component, we can see the Luma reconstruction is also adopted as a side information. With involving the copy as a network input, the model is unified to adapt to various quality levels. Moreover, regarding the filter model of the intra-slice, the partition information is involved as an additional input. The above picture shows an example of hierarchical coding structure under the random access configuration. It should be noted that intra-frames are compressed with a lower copy, so that the quality is higher than the interframes. So in the intra-frame are also more likely to be referenced by the other frames. And also the problems are happen for the interframe. When we involve the CNN-based loop filter, the reference of the frames with lower quality will change. To solve this problem, we propose the iterative training method. In training phase 1, we use a VTM encoder to generate a training dataset for intra-frame. And the reconstructed signal together with the other side information are utilized for training intra-frame filters. For the training phase 2, we want to get an inter-frame filter. So we compress the traditional videos using the random class configuration. Only the interframes are coded by the CNN-based filter, and the CNN-based filter is generated in the phase 1. So in the phase 2, the training dataset could be utilized for training an interfilter. In training phase 3, based on the intra and the interfilter generated by the phase 2 and the phase 1, we can compress the training videos under random access configuration again. Then we change the interfilter model. It's noted that the multiple training process could make the reference more close to the final state, so we can get a more higher performance. In the implementation, adaptive model selection is involved to adapt to the contents at the slice and the block level. The 3 models are in total can be selected by the encoder and the decoder. Then the model uses could be indicated by the signaled flags. Next, I will introduce the second learning-based tool, CNN-based superillusion. Discipline coding has shown the potential to improve the encoding performance. At the encoding, the input high resolution picture is downsampled and then decoded. At the decoder side, the decoded low resolution picture will be decoded, and then the low resolution picture is upsampling. It's a typical with the duration task to use the learning-based approach. Similar to the CNN-based loop filter, here we also use some side information such as the prediction copy map to enhance the network. And the residue block are also adopted as the main structure to restore high frequency signal. For the Kuma model, Luma reconstruction is involved as the side information. At the picture, we can see that with the CNN-based super resolution, the digital number is more clear to see, and the subjective quality is improved obviously, even at a lower bitrate. We evaluate the performance conforming the test condition recommended by the CLIC challenge. The coding performance is measured by the average PSNR under the limited bitrates. We also provide the experimental results in the validation set and also in the test set. Furthermore, we conduct the experiments to compare the proposed framework with the VVC, wherein the VTM11 reference software is adopted as the anchor. Bitrate is used to evaluate the RD performance. It can be obviously that in RA configuration, the proposed framework achieves more than 28% bitrate gain on average. And the rate and the distortion curves are shown in the right picture. In conclusion, we propose a learning-based video compression framework on top of VVC. It utilizes the power of the deep learning approach and also take advantage of the traditional structure. In the framework, we introduce a partition, prediction, loop filter, and super resolution tools to improve the coding performance. The results show that the framework provides higher performance compared with the VTM. And for the CLIC video track, the proposed framework achieves higher quality. Thanks for listening.
Thanks. Let's give a round of applause.
Thank you.
We again have time for one or two questions if we have one either in person or in Zoom.
Okay.
Okay, thank you so much for your talk again.
There's a question.
Oh, there was? This, okay. We also try to use ECM, however, ECM has higher complexity than VTM and takes longer time to encode. In 1 megabit per pixel track, how do you choose appropriate QP or reduce complexity in a limited competition time?
Actually, we use a fixed copy, and around the copy, we select the multiple copy. Then at the last, we choose one.
Great, thank you.
Okay, thank you.
Next up, we have our invited speaker, Zhao Wang. I believe he might be having some network difficulties, so we'll see if he's in the Zoom or not.
I'm here. Can you allow me to share the screen? Maybe we can try that first.
Yep. You should now be able to share your screen.
Okay. Let me see. Let's see if this works.
Hello, everyone. Thanks very much for inviting me. It is my pleasure to get this opportunity to talk to some of the most active researchers in the cross field of image compression and machine learning. Today, instead of talking about perceptual image quality assessment and perceptual image and video coding, which is the topic we have been highly interested in the past years, I'd like to spend some time on video codec comparison, which is a topic I believe very important but has not been thoroughly discussed in the past. So thanks to my students Wentao Liu, Zhengfang Duanmu, and Jordan Li, they are the real contributors behind this work. There has been a large number of image and video codecs being proposed. The question is how to compare them. The classical approach to compare video or image encoders is by rate distortion analysis, because for the same rate, a better codec should produce better quality. Or in order to achieve the same quality, a better encoder should use less rate. So by drawing these quality rate or rate quality curves for two codecs, we can compare their relative performance. In particular, we can compute the quality gain or the rate savings as shown as the shaded region in these figures. So in order to perform rate distortion analysis, the first thing is we need to have a better quality model Q. This has been a research topic for many years, and we have spent a lot of time, a lot of effort in this field. And so far, we do have quite some available quality models that we can use to evaluate video quality. But that's not the end of the story. The second thing that we also need to have a way to do a fair evaluation of the quality gain and the rate saving. And this is the video codec comparison topic we're going to focus on in this talk. In the video coding industry, the most widely used method for video codec comparison is called BD-PSNR or BD rate. So suppose we are given two video codecs. For each codec, we first create samples. Typically, we have 4 samples of rate and PSNR pairs by doing multiple times of encoding and followed by decoding and quality assessment. So this is typically the most expensive stuff in the evaluation. So after that, in step 2, we do a cubic polynomial fitting from R to PSNR for each codec. And then we do cubic polynomial fitting from PSNR to R for each codec. And then we produce these curves. Then we can compute the quality gain or BD PSNR or the rate saving called BD rate based on these curves. The BD approach was originally designed assuming PSNR is the video quality metric, but in the past decades, more and more video coding engineers realized that PSNR is not a very good predictor of perceptual video quality. And these days, more and more engineers are adopting some perceptually more meaningful video quality metrics such as SIM+ and VMAP, which are pretty frequently used in the video coding practice these days. So then the question is whether this BD approach can generalize to these other video quality models. As shown in this example, unfortunately this is not the case because when BD approach have a good fitting in the case of PSNR, it sometimes produce very poor result in modeling the curves for SIM+ and the VMAP. Another drawback of the BD approach is that it cannot guarantee monotonicity. So even though when the samples are monotonic, the fitting curves is not guaranteed to be monotonic. So especially in this new codec case, in this case we have SIM+ and VMAP. As you can see, the fitted curve are often not monotonic. Another desirable property of a video codec comparison tool is that we expect it can produce a consistent result between quality gain and the rate saving. Because if one codec is better than the other, then we would expect the first codec to produce both quality gain and the rate saving over the second codec. But this is not always the case for BD analysis. For example, in this particular example, the BD analysis is predicting quality gain based on quality rate analysis, but it doesn't produce any saving in the case of rate and quality analysis. So this is far from the ground truth. As we can see, in the case of ground truth, the codec 2 is better than codec 1 in terms of quality gain, and at the same time save a lot of rate. And this is not shown in BD analysis. And here is another example. Again, the BD analysis is showing conflict result between quality gain and the rate saving. Actually, it is saying there's no rate saving, and this is far from the ground truth. In the case of ground truth, which is produced by dense sampling, by doing compression at many points throughout all the curve. When we observe the ground truth, actually the rate saving is huge. It's 55%, which is not predicted by BD approach. For a really good video codec analysis tool, we also would like it to be able to extrapolate. In other words, when we have a few samples and then we draw a RD curve out of the samples, we would expect that the curve is making some meaningful prediction beyond the sampling point, especially outside the rightmost sampling curve. And unfortunately, the BD approach is not creating such a meaningful curve as we can see in this example. Recall that in order to create rate distortion or distortion rate curves, we first need to create samples. So for each of these samples, we need to take the video, do encoding and decoding, followed by video quality assessment. So even to create one sample is an expensive process. For the BD approach, typically we need to use 4 samples to create one curve. So the question is, can we improve the efficiency? What if we reduce the number of samples? What if we only have 3 samples? So here we're showing an example. When we reduce the samples from 4 to 3, the log cubic fitting by the BD approach really failed to produce a reasonable rate distortion rate curve. So based on the previous observation, we can make a wish list for video codec comparison tools. So we want this VCC tool to have good generalizability to a broader range of VQA models. We also want it to have monotonicity in producing rate distortion and distortion rate curves. And we also want it to have consistency between the evaluation of quality gain and the rate savings. And we also want it to have the capability to extrapolate beyond the sampling points, limited number of sampling points. And finally, you want to have high efficiency. In other words, we want to have the best rate distortion estimation with the fewest possible number of samples, because the samples are super expensive. From the previous analysis, it seems like the BD approach does not satisfy this wish list, especially when we apply the BD approach to novel video quality assessment models such as SimPlus and the VMAF. So that's why we have a call for better video codec comparison tool that can satisfy all these conditions, hopefully all at the same time. In order to better characterize the performance of video codecs over different types of video content, my student Wentao Liu and Zhengfang Duanmu, they proposed a concept called generalized rate distortion analysis, which allow for additional coding parameters to be added into the picture. So in this particular example, we add resolution into the picture. So instead of a RD curve, we have a 3D surface of quality rate resolution. So they also developed a method called eigen GRD approach, where they use a pretty simple component analysis to create eigensurfaces, and then they find coefficients associated with these eigensurfaces with some additional constraints such as axial monotonicity. So in the end, the purpose, there are two purposes. The first is to maximizing accuracy. So we want the fitting surfaces by combining these eigen surfaces to be a very good approximation of the ground truth. The second thing is that we want to maximize the efficiency. In other words, in the future, we only want to sample the whole surface by a few points, and then we can still have a very nice model, a very good approximation, producing a surface that approximates the ground truth very well. And of course, here we're showing a 3D example, and 2D is just a special case. It's easily kind of reduced to the 2D case. Now let's observe how a reduced version of EGRD approach applied to predicting rate distortion and distortion rate curves. As we have already seen before, in the case of the BD analysis, the BD analysis failed to perform when the VQA model is not PSNR. In this case, we are using SIMPLUS as an example. As we can see, the BD method performed poorly to model the bit rate and quality curve. Instead, the EGRD approach producing very nice prediction of the ground truth. And a similar result has been observed when we applied the reduced EGRD approach to VMAF as the VQA model. And again, this is a lot better than the BD approach. Another good property of the EGRD approach is that it can enforce monotonicity, which is a property that applies to most of the good video encoders. So in this particular example, the BD approach fails to produce monotonic curves, but EGRD is very successful at doing that. But at the same time, it also provides a very good fit to the ground truth. Perhaps not surprisingly, the EGRD approach is also producing very good consistency between quality gain and the rate savings. So this is an example that we have shown before for BD approach. In the case of BD approach, we got a straightforward conflict between quality gain and the rate saving, which is far from ground truth. But the EGRD approach is not only producing a consistent approach, but produce a very good approximation to the ground truth. And here is another example where the video quality model is VMAF rather than SIMPLUS, but the conclusion is very similar. EGRD is producing a lot better consistency between quality gain and rate saving than the BD approach. EGRD has also demonstrated very good capability to extrapolate. In this particular example, the EGRD is making a lot more reasonable predictions than the BD approach. So beyond especially beyond the rightmost sampling point, and also produce better approximation of the ground truth. In this example, only with 3 samples, the EGRD approach can still produce very reasonable rate distortion and distortion rate curves, and actually provide a good approximation to the ground truth. So this is a big advantage over BD approach, which fail pretty badly in the case of only 3 samples. Talking about the sampling efficiency, the advantage of the EGRD approach actually is a lot bigger when we talk about fitting the whole GRD surface, 3D GRD surface of a quality rate resolution. Imagine that if you want to produce the video content at different resolutions, and then in order to characterize the rate distortion performance using the BD approach, we have to sample 4 points at each resolution. That end up with a lot of points for the whole surface. That will be super expensive. So in the EGRD approach, because we have the eigensurfaces, it is possible to use very few samples in order to produce the whole 3D surface. So how about we only use 4 points for the entire surface, and this how the EGRD approach works for in this case. And here is how the EGRD eigen analysis method work to kind of predict real-world GRD services. The top left corner is the mean GRD service, and the rest of the figures are eigenservices that are used by the EGRD approach by combining them in order to produce predictions of a real-world GRD services. And of course, in the case that we only have 4 samples, we produce 4 coefficients, and then we only use 4 eigensurfaces to make the GRD surface prediction. And here is an example of fitting an entire GRD surface from only 4 samples based on the EGRD approach. Once such a surface is produced, we can also perform 2D slicing at each of the resolution. That will produce a lot of 2D RD curves, as we can see on the right-hand side. So in some sense, we can think about this EGRD approach as a very efficient method of producing many RD curves, each for the same video content but for different resolution. A very interesting additional observation is the connection between the group of RD curves created by this EGRD approach and the convex Haar structure proposed by the blog, Nextly blog on partial optimization. So basically in that blog, it is saying that if we have a video content and we compress that the same content into different resolutions, then when we put the RD curve of this content at different resolution on the same figure, then we should see these interesting structures. So basically for high resolution content, when the bitrate is high, then the quality is pretty high. But because the high resolution content is much harder to compress, when bitrate is getting lower, the quality drops faster. So for mid-resolution content, the quality when bitrate is high, the quality is at mid-range, but relatively when the bitrate is getting lower, the quality drops slower. But for the low-resolution version of this, the starting point at high bitrate, the quality is not that high. But because it's low resolution is relatively easier to compress, the quality drop slower when bitrate get lower. So if we put different resolution of the same content all together and observe all the RD curves, then we see this general structure. And all these RD curves will be covered with an envelope which has this convex Haar structure. So that's a very interesting observation when we compress the same video content at different resolutions and observe the RD curves. And this behavior is exactly what we observe by fitting this EGRD model into some real-world content as shown on the right-hand side. So this shows that the EGRD approach is not only producing something that producing good fit to some real-world data, but also recreating this very nice theoretical structure of this convex Haar structure through this detailed analysis. In conclusion, the current video codec comparison tools, such as the BD rate, lack some desirable properties. These include the generalizability to video quality models other than PSNR, the monotonicity of RD and DR curves, the consistency between quality gain and the rate saving predictions, the capability to extrapolate beyond sampling points, and the sampling efficiency. The EGRD approach shows some good promises as a new VCC tool. So we have put the EGRD tool at GitHub, and the link is here. It is very easy to use, and you are very welcome to play with it. Thank you very much.
Great, thank you for your presentation. We should have time for a couple questions. Irfan, did you have a question?
No, I didn't have a question.
Okay, I just saw the reaction.
I was using a reaction clock.
I think I got a question from the chat.
Yes, we have one from Phil and over Zoom. How does EGRD guarantee monotonicity?
Okay, that's a very good question. So that's something related to the optimization. So it is an eigen approach, but it's not like a straightforward projection, like the typical principal component analysis in when we try to find the coefficients, because we want to add these axial monotonicity constraints. So the surface, if we slice for each individual resolution, we want each one of them is like a monotonic curve. So that goes to the optimization procedure. That goes to actually one of the paper I'm showing. There is a paper on attributed transaction image processing that tells exactly. There's actually a few other constraints as well. So in that fitting, we also kind of assume like C1 continuity kind of constraints. So we put all these together. So probably it's better to look at those papers. And other than the eigen GRD approach, we actually have another approach that's published in another attributed transaction on image processing paper. So they're both in the slides. Maybe it's better to look into that because it's a bit complicated to explain here. Thanks.
Great. One more time, thank you.
Thank you.
We're going to move on to the perceptual quality talks. The third place talk could not attend. They are Team King's Lair. And let me find their submission. Their paper is Focused Feature Differentiation Network for Image Quality Assessment. And you should check that out on the proceedings. But I believe we do have the next perceptual metric talk. It should be team IQALY. Is team IQALY from Alibaba in chat?
Hello, can I be heard clearly?
Yes, we can hear you now.
Okay.
I just gave you permission, so you should be able to present as well.
Okay, thank you. Okay. Hello, everyone. I'm Yulian Wei from Alibaba Group, and
we're actually not getting anything on the screen share. It is black for us.
Can my slide be seen?
Yeah, we're still not seeing it.
Still cannot see?
Not on our end. If anybody else can see it in the Zoom, it might be a local issue. Okay, now we see it.
Okay. Hello, everyone. I'm Yulian Wei from Alibaba Group. And firstly, I would like to thank the organizers for this great competition and give us such an opportunity to present our work. And today I'm here to share my work in perceptual quality track named Soft Ranked Index Fusion Framework with silencing weighting for image quality assessment. And my presentation mainly contains 3 parts. Firstly, I will introduce the perceptual quality task for those who may not be familiar with this track. I'll introduce some related works in CLIC 2021. Since I'm a newbie in this area, most of my explorations are inspired by these excellent works. Lastly, I will introduce the methods adopted in my work and our final results in validation phase and the test phase. The perceptual quality track in CLIC is slightly different from other perceptual quality tasks. The only goal of which is predicting more scores from input images. In our perceptual quality track, we have to design a metric to rank the images from compression task. That means when fed with an image pair, we have to predict if the compressed image A is better than the compressed image B, or conversely. And here are top 3 approaches in last year's perceptual quality track. MMFN adaptively rescales the predicted quality from different metrics and regresses a single scala as the final score. DPRS is inspired by DSTS, which is a recently developed full reference IQA model. DPRS considers feature similarity on both pixel-wise and gradient-wise. ROI perceptual metric takes advantage of silencing regions and fuses different types of metrics. As can be seen, fusion-based methods shown its advantage in last year's competition, and most of these works introduce additional information to boost their performance. There are different techniques that we adopted during our exploration, including data cleaning and dataset selection, enhancing existing methods, introducing additional information for fusion, exploring new ways for utilizing silence information, and other. Since our framework is trained with a preference prediction task and another quality assessment auxiliary task, different training sets are chosen for these 2 different tasks. For preference prediction task, CLIC 2021 test dataset, which is released by the organizer, is selected as our training set. Records with opposite labels or records that none of our 9 predict the preference correctly are removed. In total, 96,036 pairs are chosen as our training set, and 24,009 pairs are chosen as our validation set. For quality assessment task, we have tried different datasets. As can be seen, model trained on PIPAL dataset has the highest accuracy, and therefore PIPAL dataset is selected as our training set. since the most scores of PIPL are derived with the rank model, which quite meets our final goal. We believe that's why model trained on this dataset achieves the highest performance. DRSTS, which is also the fundamental structure of DPRS, has also been explored in our work. Original DRSTS utilizes pre-trained VGG to extract deep features, and these features from different stages are weighted to predict the final score. In our exploration, we try to replace VGG to other classification models. Interestingly, DRSTS with ResNet 50 as its backbone model has the highest accuracy, even compared with EfficientNet or DenseNet. Besides, we remove the features from last stage since performance drop can be observed when utilizing the features from stage 5. For preference prediction task, we believe that rank information or input images behind the predicted scores of different measures are more important than the predicted scores themselves. Therefore, instead of directly infusing predicted scores from different measures, soft rank indexes, which indicate the rank relationship of the input images, are derived with an adaptive Bradley-Terry model for further fusion. As can be seen in the table, directly fusion predicted scores do not perform well, and the fusion with only 0 or 1 preference label has a slight performance gain. Compared with these two fusion methods, our fusion method with soft ranked indexes achieves the highest accuracy. And inspired by the ROI-based metric, we also try to explore the new way for utilizing silencer information. Two different silencer weighting approaches have been evaluated. The first one is the silencer weighting on the score map. In this approach, a per pixel score map is first calculated for a certain measure, and then weighted by the detected silencer map to generate a final score. In the other approach, the input images are directly weighted by the detected silencer map and then fed into measures for quality score computation. In our experiment, silencer weighting on the input images has a more significant performance gain. According to the aforementioned methods, we form our final framework. The silencer weighting model introduced additional silencer information, and the soft ranked index mapping model converts scores of different measures into ranked information for further fusion. And the multi-index fusion model fuses soft ranked indexes and generates a final preference prediction. And in the validation phase, the accuracy of our method is 0.792, which is almost the same with the second place method. And in addition to aforementioned methods, another two tricks have also been utilized for our final submission. The first one is test time augmentation, TTA. TTA aims at boosting the model accuracy by using data augmentation or the inference stage. In our case, resize with different scales and multi-crops are chosen as our augmentation methods. Multiple predictions are generated for one image pair. Voting is utilized to generate a final prediction result. And can be seen in our experiment, TTA can achieve an additional performance gain. Human raters rate the images in different distances and different scales. We believe that our model with TTA can generalize better under different circumstances. Another trick is adversarial validation. Since we have multiple official datasets, including CLIC 2021 test set, CLIC 2022 test set, and CLIC 2022 and 21 validation set, we wonder if these datasets have similar quality distribution. If a training set and a test set have different quality distribution, models trained on training set may not generalize well on test set. We utilize DRSTS score difference as a criterion of image pairs quality difference. left graph shows the quality difference tendency of different data sets. And it can be seen different years validation set and test set have different quality distribution. The image pairs in CLIC 22 test set, which is the orange line, has a relatively larger quality difference, which means that this year's test set have fewer hard samples than last year's. To overcome the quality distribution mismatch between training set and the test set, adversarial validation is adopted. Firstly, we mix the samples of CLIC 2021 test set and the CLIC 2022 test set. Then a simple classification is trained to clarify if the sample pairs come from CLIC 2022 test set or CLIC 2021 test set. Next, the hardest to classify samples from CLIC 2021 test set are chosen to form our final validation set. As can be seen in the left graph, the new established validation set, which is the red line, has more similar distribution compared with the CLIC 2022 test set. Finally, the best model can be further selected based on the performance of the new validation set. And here is the result of our framework in test phase, and it can be seen with aforementioned approaches, including metric fusion with silence weighting, TTA, and adversarial validation. The accuracy of our framework achieves 0.805, and more experimental details can be found in our paper. And that's all. Thank you.
Great, thank you. We've got time for a few questions. I guess I have a question. Can you give some more details about the adversarial differences you saw in the CLIC 2022 data set versus the previous years? I know we try relatively hard to make sure that we don't have sort of changes in complexity, but we obviously didn't use the metric that you did.
Okay. Can my slides be seen?
We cannot see them now.
Can you see it now?
Nope.
That's weird. Wait a minute.
Now we can.
Okay. Actually, we utilize the DSTS score difference as a criterion of image pairs quality difference. That means when we are fed with image pairs containing original image and two compressed images, we calculate the DSTS score for each compressed image and calculate the difference. And we have done the same operation on CLIC 21 test set, CLIC 22 test set, and CLIC 21 and both CLIC 22 validation set. And the results are shown in the figure in the left figure. And the orange line is the quality distribution in CLIC 22 test set. And as you can see, different years quality distribution are all has slightly different. And the orange line, the near zero quality difference is relatively smaller than last year's, and which means that the quality difference of CLIC 22 test set is relatively lower, and there are fewer hard samples in this year's competition's image pairs. And I guess it's the phenomenon can be observed in the final result. In last year's competition, the top one accuracy, I don't remember the exactly number. It's something like 0.7449. I'm not sure, but this year's accuracy all reaches above 0.8. I guess that's something can also demonstrate this phenomenon that this year's test set have fewer hard samples, and metrics can have a higher accuracy compared to last year's samples.
Okay, I think George also has a question. How many samples from your training set were selected as coming from the CLIC 2022 test set? And did you visually inspect the output of the distribution samples? Was there any obvious visual difference?
It's like 1,000 or nearly 2,000 samples were selected as coming from CLIC 2022 test set, and the threshold is based on the quality distribution. If we have larger threshold, then more samples can be selected as our new validation set, but the quality distribution may be not that similar as in the CLIC 22 test set. So it is in
I think you cut out there at the end.
Sorry, it has been disconnected.
Okay, we can hear you now.
Yeah. And do you visually expect to see this out of distribution samples, or is there any obvious? Not exactly. It's just it's easier to figure out which one is better, but no obvious visual difference in my case. I wonder. Yeah.
Okay, great. Thank you again for your talk.
Okay, thank you.
We're moving on to our last perceptual metric talk from team IMCL T1.
Yeah, I'm here. Can you hear me?
Yep, I can hear you. Let me give you present permission, and you should be able to present.
Okay.
And we can see everything just fine.
Okay. I'll get started. Hi, everyone. I'm Yan Dingpeng, and I'm from University of Science and Technology of China. And I will present our solution for CLIC 2022, swing accurate, learned swing distance for compressed image quality assessment. So let's first introduce our motivation. Image compression has raised widespread interest recently due to its significant importance for multimedia storage and transmission. And meanwhile, a reliable image quality assessment for compressed image can not only help to verify the performance of measured compression algorithms, but also help to guide the compression optimization in turn. The first part is about the quality of compressed images, and we present a few examples here. The image on the left is the reference image, and the one in the middle is the distorted image generated by HEVC codec. The one on the right is the distorted image generated by the learning-based codec. And as shown in the figure, the compression artifacts are usually non-uniform distributed with diverse types and degrees. Thus, we think it is important to combine the local and the global information to measure the perceptual quality of compressed images. And then we will briefly introduce the existing for reference IQ algorithms, which can be roughly summarized into 4 categories: and traditional, CNN-based, fusion-based, and transformer-based. Commonly used traditional IQ algorithms in image compression methods, such as PSNR, are mainly optimized to measure the pixel-wise fidelity, and the SSIM index considers image degradation as perceived changes in structure similarity. However, learning-based metric also show impressive improvement. PIPS obtains the perceptual similarity judgment by calculating the L2 distance between CNN features pre-trained on ImageNet classification task. And similarly, the DISTS index measures the texture and the structure similarity between the VGG-based deep features to calculate the perceptual similarity of 2 images. And besides, there are also works try fusing those successful metrics to achieve robust performance. And MMFM proposed by our team on CLIC computation last year, adapting fuse 10 metrics according to image content and distortion. And it performs well on complicated distortion conditions. And unfortunately, the local global information was not used on this metric, which motivated us to fuse multi-level feature this year. And recently, Transformer has shown promising potential in computer vision area and outperforms CNN measures mainstream tasks, such as image classification and object detection. IQT extracted the feature representation from a CNN backbone and then feed the extracted feature maps into the transformer encoder and the decoder. And in this paper, we proposed a for reference image quality assessment metric named swing IQA, and it was based on swing transformer. The contribution of ours can be concluded from 2 aspects. The first is that we demonstrate that the theoretical feature extracted from each stage of swing transformer have strong representation ability towards non-uniform distributed compression artifact. And the second is that instead of calculating the L2 distance feature similarity between the reference and the distorted image feature like PIPS or DIST, we designed an efficient cross-attention strategy to map the extracted feature representation into a learned swing distance space. Next, I will introduce our approach. The first is the design of the network architecture. The framework of swing IQA is shown in this figure. It consists of 3 parts. A swing theoretical feature extractor that extracts multi-scale local global feature representations, and a cross-attention block that maps the pair of reference and the distorted image feature into a learned swing distance space, and a MLP head, which maps the learned swing distance into a quality score. Swing transformer build hierarchical feature maps by merging multi-level deep features. We designed this hierarchical strategy because the compression artifact are usually non-uniformly distributed with diverse distortion types and degrees. We first extract intermediate features from each stage of the swing transformer and obtain a group of features. Then we upsample all the features to the same resolution and concatenate the features along the channel dimension to get the final hierarchical feature representation. In order to better measure the perceptual distance of reference feature and the distorted image feature, we adopt the cross-attention operation here to map them to a learned swing distance space. And here we can see it was achieved by calculating the attention between the reference feature and the reference features query and the distance features key and value. As for the chaining strategy, we first retrain the swing IQA on carded dataset, and we adopt the mean square error loss for pre-training. And here is the formulation. Then we use dataset with modes and 2AFC, or we can call it a RAM label, to fine-tune our model. Following the work of LPIPs, given two distance D1 and D2, we optimize a small judgment network G to map the distance feature to a predicted judgment score. And we use binary cross-entropy loss for training. And finally, the total training loss is composed of two parts. The regression loss from most regression and the BCE loss from the 2AFC classification. We obtain the predicted the result by comparing the distance given by swing IQA. And here we can see smaller distance represent the better quality. Then I will introduce the experiment part. And we summarize the data set we use for pre-training and training and the testing in this table. And during the pre-training stage, we only use carded data set to initialize a good feature. And on training stage, there are many data sets we use, both QFC label or most label. Here we can see the critical data set consists of image generated by visuals compression method, including both traditional codecs and the learning-based method. So in order to cover the distortion type as comprehensively as possible, we select the three another data sets, PIPL, PAPPS, and PIABPA, which include both traditional distortion and the learning-based algorithm output to train our model. And in this section, we discussed the performance of 5 different distance mapping strategies. The result on carded testing set is shown in this table. We can see that mode 1 is the most effective mapping strategy, which we do in cross-attention between distance feature and the reference feature. Thus, we use this strategy in our final CLIC model. Yes. We also compare our method with 2 traditional methods, metric, and 2 CNN-based metric, and 1 transformer-based method and the last year's champion method. All the compared learning-based methods are retrained using the same dataset as swing IQA. And we evaluate our performance on CLIC 2022 validation set and the subset of CLIC 2021 testing set. And the comparison results can be found in this table, and our method steadily outperforms other methods. Conclusion. And in this paper, we proposed a full reference image quality metric, swing IQA, for compressed image. Then we optimize, and we employ swing transformer to extract the theoretical feature representations. And then we optimize the cross-attention operation to map the pair of reference and distorted image representation to the learned swing distance space. And following the extensive experiment have demonstrated the effectiveness of swing IQA for the perceptual quality assessment of compressed image. Yeah, and that's all I want to talk. And thank you for your listening. If you have any question, you can let me know.
Let's just give a round of applause. Looks like we have one question in the Zoom. George asks, how did you avoid overfitting? The data set seemed rather small given the amount of information per image pair.
How did you avoid overfitting? Sorry, I will share my screen again. Here we can see we use so many just data set. Like PIPL, there are 29,000 image pairs. So I think the size of the data set is big enough to overcome the overfitting problem, because we just used the swing-based model. We didn't use the swing-large model. So I think this data size is enough. I don't think there is an overfitting problem.
And we had one more question in the chat. It is about the CLIC 2021 tests, the subtests, and how did you filter samples for that?
How did I filter the samples? Yeah, CLIC 2021, that's the subset. We because just the organizer just released the label of the CLIC 2021 test set. So we just spread part of about 20% of all the test image as test set, and the left 80% for training. And the precision of the method is random. So we didn't just consider too much, because there is no any other labels for us to instruct or expression of the set. So we just choose the simplest method, random select. Yes.
So randomly select 20% for test, 80% for training?
Yes.
Okay, perfect. Again, thank you very much. We're going to go take a short, let's call it a 10-minute break. And then when we get back, we'll do the panel discussion. Okay. Let's get started with the panel discussion. I just had a few example ideas here for discussions. Oh yeah, I'm going to invite up our previous speakers. We have a couple on the Zoom call and some CLIC organizers to come up for the discussion. Yeah, go for it. Oh, I'm gonna stay and pass it around. Can't exactly see the Zoom and questions at the same time. Hey, George. So yeah, I'm just gonna maybe seed it with a couple questions, and if anybody who's attending either here or in the Zoom has something they want to ask the panel, go ahead and line up at the mic or put a question in the chat.
Maybe you can just copy the questions on the slide in the chat and just show the chat.
Yeah. So one topic that was brought up over and over today was sort of a compute realism. Well, that doesn't copy and paste well at all. One thought for the future is, can we impose a tighter runtime limit, either limiting us to a smaller GPU or a single CPU, or should we be specifying either some amount of flops budget or an even tighter runtime restriction? And I just wanted to sort of get everybody's thoughts on how important is runtime and computation in the future of these sort of competitions and the compression field.
Sorry to start with, but I'm not one of the organizers, so I'm getting much better to answer that question. The way I feel about it, yes, compute is important, but like also mentioned in the talk today, sometimes going to high compute or reasonably high compute just to see what is possible and then scaling it down further is also a very effective solution. But I'll leave to the organizers to comment.
Yeah, I think I would go the opposite way and see how fast you can make the APUs. And or how many times faster so that you can do this. Instead of limiting the computation.
So I think this year's results have shown that you can do very well with limited compute. And that's probably an argument for, if not, directly limiting the compute, that's maybe a bit excessive, but either having 2 tracks or selecting a winner between the cortex that are below a compute threshold if that winner is not already over a winner, could be a good idea.
I guess for me, it's hard to know what to measure. I like Quantum's approach of just putting it on a device and measuring actual runtime. I'm personally not super convinced that flops is the thing we want to measure. From hearing that memory access can matter much more. So I'm a fan of measuring actual runtime, but I don't know which device. I was a bit surprised by Debarka saying that he doesn't think we should use neural engines. It would be nice to have it here, but I don't think it's here. Yeah, I think actual runtime measuring makes a lot of sense.
Yeah, so on whether we add it to the challenge itself, I need to think about balancing the difficulty of participating versus how predicted what we measure is reflects what's valuable. So to make this more concrete, we don't want to put a lot of work on the participants to just engineer the runtime on the particular environment, and we have, unless that's reflective of what we would see on other devices. So that makes it a bit hard. If like we have one type of GPU, it's running in a Docker environment, in Google Cloud, etc. So how can we measure it so that it's not too hard and not too engineered just towards our platform?
Yeah, George, did you want to comment on this?
Sure. I wanted to mention something which is very concerning, as it is, if we count flops, we have a lot of problems with respect to accounting for serial versus parallel steps in models. For example, in transformer-like models, there's this issue of maybe needing to do some autoregressive steps, which might require multiple trips to see GPU or TPU. So just having a single number might be a bit hard, especially since it will have to be, in some sense, self-reported, because I don't know how we'll be able to compute the flops per pixel in a reliable manner for all participants, especially given that we don't require a particular frame. So I'm very unsure about the flops per pixel direction. And I also am quite concerned about measuring runtime, because this is very much vendor specific. But we need to do something if you want to encourage speed somehow. So I'm not exactly sure how. We currently measure runtime. So maybe we can keep doing that. I don't know what's the best.
So one other thing we had brainstormed about changing in the future is potentially having a year-long running contest for the servers, where people could submit sort of more naturally or at the cadence of their research, and then something like CBPR or this workshop would be one checkpoint in a year, and not sort of a 3 to 4 month sprint for their work. What do you think about that, George?
Well, obviously, I think it's a very intriguing idea. It has some pluses and minuses. On the plus side, there's no rush to make a particular deadline. You are always coming up with something, you can test it at your leisure. And when a new CLIC comes, of course, you can just already have your best model prepared. You don't have to do anything. The only question is, if we have the test set available year-round, or more likely a validation set, it is very possible people will train on it. And I don't know if this is something which we need to be worried about or not. I think it's up for debate, but in general, I think it will be still positive. People to track performance as a function of time for all participants.
Well, there is this solution that we used once for the keyframe challenge, where we kind of just made the test set humongous and then evaluated on a random subset, similar to kind of column growth complexity. So we did do that once for the keyframe challenge, where basically the test set was available the whole time. But yeah, but I actually wanted to comment that please come to the microphone, ask questions, and add your thoughts. Yeah.
Yes, actually, the purpose of this panel discussion is to ask for feedback from the audience with some ideas on how to run the next year's challenges, actually.
go there or
Whatever's closer.
Hello. So my question is very simple. Is there a plan to add a track for video quality? And where is it?
Do you wanna?
So you were asking about a video quality assessment track. And yeah, that was one of the, we kind of brainstormed a few things we wanted to do for next year. Video quality assessment is huge up there. We've gotten a lot of interest in the image quality, and it's clear from Ross's presentation, the amount of time and money it takes to get video ratings can be quite expensive. So there's a real strong need for having a highly correlated video quality metric. And I think we're well positioned to offer this as a competition. Maybe, I don't know, Ross, do you have any thoughts on it?
Yeah, so we're going to have a lot more data available. So we're having a training data set, and we should offer this. I also like the idea of having a continuous challenge, and not just once a year. So something like this we could have as a continuous challenge.
An interesting question related to continuous challenge is whether we also want to do continuous, smaller scale subjective evaluation of. This is practically significantly more complicated, of course, as one would need to deal with human raters and whatever else. But I mean, I guess one question I have is whether that's something you would be interested in as participants.
Yeah, that's right.
And that could also fit in continuous quality assessment challenge, because then the data that comes in from the continuous assessment challenge can be used as a test set for the participation, for the quality set.
Yeah, something we also thought about as far as running a video quality challenge and keeping the servers up sort of year round is having community raters. So having the possibility of you logging in to one of our rating sites, seeing other people's methods like 5-10 second clips, and giving your own perceptual evaluation. One of the benefits is that I think many people in the community were probably already pretty well trained. We're very sensitive to the type of artifacts that we see. I think it's just going to be better than sort of the random mechanical Turker. And you get some pre-training, and there's a sort of, there's a value to doing this, because you're going to submit your method to get evaluated. Other people are submitting theirs. So it's just part of building a community to sort of get these ratings as we build out the methods more. Fabian?
I don't have any. But I mean, there will be technical challenges involved in running this server. Remains to be seen how we can do that.
Hi, just out of curiosity, so do you have any thoughts of expanding the scope of the challenge to also include encode time? 1 year, maybe perhaps not next year, but maybe a year. That will be part of the challenge.
Well, I can add that we have, like, maybe to take the example that George mentioned before on entropy coding. So when you just look at, actually minimizing runtime, you might be running the transforms on an accelerator, but typically entropy coding needs to run on CPU, and just to make sure that you can transfer the context efficiently, like all these kind of device transfers, etc. They are kind of platform specific, and unless we can settle on a way to measure speed in an accessible way, and like that's the problem we have, whether it's encode or decode speed. That's something we could do at the same time if we figure out like, how to actually measure it. I don't know if anyone has a concrete suggestion on how we could do it.
Yeah, so I've run about 10 challenges in the speech area, and they've had basically real-time requirements. We've had both real-time tracks and non-real-time tracks. Surprisingly, the non-real-time tracks don't get much traction. So the way that we make it available is we standardize the platform that we need to run it on, and we're basically just measuring wall clock time. So that takes all the system level benchmarking into account. Counting max really isn't that useful.
It should be good enough.
One other thing maybe also take into account is that most of the codec failures you see because of a low delay setting, like this frame setting for real-time video. But as soon as you go to streaming, then encoding time becomes a lot less important for this type of stuff. Because you can do things like fertile encoding, you just take a very long time or overfit to a particular video. And then decoding time is actually the most pressing part, making sure that the decoder runs with very low context.
Yeah, I also agree that decoding time is probably more important. I don't know, like, I mean, if we can figure out, you know, whether the platform we decided on a platform that we can agree is standard enough, whatever that means, that we are okay at defining that one as the type of platform for the speed requirements. It may be that we don't do an encoding limited challenge. Maybe the encoding speed limit challenge. Maybe we will. I'm not sure, but I think decoding is the more pressing concern, at least in the near future.
Yeah, so just thinking a bit more about the runtime side, like one kind of compromise or a step in the right direction might be to just add more constraints. So, you know, instead of making the runtime a metric that you compete on, then you start to over-engineer towards the specific platform, just kind of adding a bit more constraints. So maximum runtime being closer to something that's reasonable, but maybe not so tight that you really need to fight for every millisecond. That might be one way to progress here.
Well, the problem of doing it that way is that it's a symmetric problem, right? If you have margin, then you can put more things in the codec until you reach the margin, and then you get back into optimization. So to be fair, it's probably a reasonable solution. Like, I don't think it will be possible to completely eliminate the effect of, you know, accurate engineering, but it should be feasible to at least make it. Like, for example, if we put a limit on 10 times the time it takes to BBC to decode images or something like that, it should be maybe not 10, maybe 5. It should be enough to constrain a subset of the codecs to a more reasonable running time, while I mean, we have proof that it is possible to achieve excellent results within those constraints.
Yeah, maybe I can maybe also just add to that comment, I guess, some feedback on in the runtime. I do think that it becomes important, especially when considering what we should incentivize for future research. And if we keep not considering runtime into the competition, then there's no incentive really to chase faster models with faster inference. It just create big content models, and it just feels like we're going sort of the wrong direction. So I do think that's just my addition to that discussion.
No, I totally agree. We did actually measure at least decode latency. I think back in 2018, what we saw at the time was every method that was based off BBC was very fast, and every neural method was very slow. So I guess maybe that is pushing. We were afraid that we were going to push everybody into do a post process or an in-loop filter on BBC, and not to explore sort of new methods. But I think you make a good point. We do need to put compute and/or runtime in the equation, and we just need to find a way to do that sort of properly incentivizes a lot of new diverse research, and not like I don't think what we want to see is every submission next year being a transformer. We want to see new and exciting things, but we also want to see things that can eventually be deployed.
I think learned image compression has probably gone a bit further than in 2018.
Oh yeah, definitely.
There's a lot has to improve.
The particular.
Yeah, and I like what Ross said about having a fixed platform for measuring these. I think that'd be a great idea to find something that's sort of commonly available worldwide, maybe an embedded platform. Maybe we can get something cloud-based that is, available in all regions, so that we can have all the participants actually do these locally. Because sort of the worst thing to have in the competition is have somebody have a method that works on their machine, and then it's ran on the cloud or it's ran on a different GPU, and then all of a sudden we have a whole other set of debugging to do. So definitely. Oh, George?
Yeah, I guess I wanted to sort of address two things. Thing number one, on the encoding. If we are to take encoding time into equation, I don't think we can measure it in the same way we measure decode, simply because of an IP standpoint. I don't think it's reasonable that any company or any institution or any university would want us to run their encoders on our servers because of IP concerns. And I don't think Google or whomever is hosting this competition would want to do that either for the same reason. So basically, I feel like encoders are things which we don't want to know about. I don't think you want us to know for literally the same reason. So what's it means is that if we're going to do an encoding time entry, we're going to have it be self-reported. So basically, we'd have to essentially we can trust be truthful about the time. Or as was suggested, to have a widely available platform and just say, hey, run it on of this platform. I'm not sure if this is super reasonable, especially because universities, which might not have to buy it, for example. So I'm still very optimistic to offer encoding time measurement for this competition. Now, on the decoding side, as I said, we are measuring this is not a problem. But what happens is we need to come up with a way. Number one, doesn't discourage universities from participating. I think this is an important aspect of our workshop. We want to encourage more research to happen. So in general, I think universities don't tend to focus too much on runtime, as they just want to focus on what's latest and greatest. So we would have to come up with a different set of prizes for speed-based rankings. But the problem is that if you want to gamify this axis, you can come up and just submit the JPEG decoder, and you'll win probably the competition because that one is very fast. So the alternative would be maybe to have like a Lagrange multiplier between speed and rank on the unrestrained sort of competition. So I'm not sure. Any proposals here would be welcomed. Whoever else.
I mean, on the last part of saying that it can get to people, somebody check the decoders, I think the suggestion of just having a constraint and then still measuring only PSNR by itself is like just saying on video side that we want 10 FPS decoding, and that's the constraint. I mean, we don't know what the platform will be. If we had one, I think that would be a reasonable setup.
Yeah, in a way, we could imagine rectangling like bitrate. So we could even go back down to 1 bitrate, and then have 3 runtime constraints. But, 10 milliseconds, 100 milliseconds, 1 second, or whatever is reasonable.
Yeah, then you can do a curve on that. Would be interesting.
So I wanted to add one more detail, as it is, I don't know how to think about what the Varga was talking with respect to runtime requirements, especially for video, because they are so stringent that we are talking about a factor of between 100 and 1,000 less compute per pixel. So, for example, if somebody has a solution which is your typical classical codec plus post-processing, is this something which would be interesting? Would it be interesting to have a track for this, maybe? I'm not sure. I just want you to try to see if this might be actually a good idea, because I think as a post-processing, it might be possible to achieve the targets that he was talking about, for example. But I don't know about end-to-end video, learned video compression, achieving it in the near future.
So one thing to keep in mind is that, as far as I understand, the Varga's constraints were related mostly to what would you need to deploy neural compression in a hardware video decoder today. While probably it is feasible, to do TPU-based decoders or GPU-based decoders that don't have the same constraints, because I mean, the hardware-based implementations have the constraint that they can't use existing hardware, while a software-based decoder wouldn't have that constraint. So that's something to keep in mind. I don't know what that means, like whether we should try to keep that constraint in mind and have a separate track for that constraint, or whether we want to, I don't know.
I wanted to direct the question to Ork, because like we saw that talking about these 1,000 flops per pixel or so constraints, and then Ork was presenting us neural video codecs running in real time on a device today. Like, how do you reconcile these massively different points?
Let me try to comment on that. I think I'm mostly on Rosa's side here. I do believe that the hardware, as it improves and as it gets itself, that you'll have to worry less about compute than you do now. But I mean, the overarching theme is just neural codecs are more expensive than dedicated hardware codecs. And there's clearly no real way around. In some of these efficient codecs, as we've shown here, this transformer-based codec, I believe, is still in the 250K max per pixel range. So that's 50 times higher than the bar I found reasonable. We will get there, obviously, but it requires a lot of manual work still, and making sure that these codecs are so cheap to run on the device. It's not trivial work either. I don't know if a track that focuses on ultra low compute is very sensible at this point. But in all the suggestions you made regarding compute make sense, and you're already constraining it in some shape or form. Maybe I can ask a question, sir. Do you think that there are other things that CLIC could be doing that are more focused on, real life use cases for making codecs practical, other than compute, which we discussed, and image and video metrics, which there already are tracks for?
So in my mind, the main constraints are runtime. Then maybe second to that would be determinism, which I don't know how you would do a specific track on that or a challenge. I mean, apparently participants are managing to do deterministic decoding, otherwise they would get results. So I don't know what other practical concerns there are. I think for me the runtime is really the biggest thing that we are obviously not there yet. In what we optimize.
Yeah, I think the fact that we do run a user study to determine the winner, does go a long way towards trying to target compression that meets the needs of users. I guess it would be interesting to understand, like, if there is a gap between the type of user studies we run in this kind of constrained environments and, compared to how people use media and realize very often on their phones, all kinds of situations. I guess we're heavily biased towards kind of desktop computing, while the rest of the world is spending 90% of their time or something on all these mobile devices. I think that might be an aspect.
So, possible idea which has been running in the back of my mind for a while, but who knows? In particular, who knows if this would be practical as a track for a competition like this? Just random thought I had, which may be interesting, is a track focused or a competition focused on creating neural encoders for traditional codecs, which on one hand very simply solve the problem of like being able to actually use these things in production or in real world, because well, you can already decode traditional codecs. On the other hand, it's traditional codecs are complicated, as Sebastian was saying. So I'm not sure that the amount of work that would be involved in it would make it. I mean, sure, we can all target JPEG as a decoder, but does that leave enough room to actually do something meaningful? I don't know. And if we switch to more complicated decoders, is it feasible in 1 year to? Is it a reasonable project for a competition? I don't know. I didn't do any kind of feasibility study on this.
I think in general it's interesting to explore this, maybe more so for video than for images, because we don't know what the margin there is. There was one paper from DeepMind that was optimizing a DP9 encoder. I think they got like 10% rate reduction, quite significant, or something in that order. Maybe in a more general note, Eric was saying earlier, it would be interesting to have an easy interface to these codecs. For me, it's always like, you want to look at HEVC, you find some, I guess, C++ code, and you have no idea what's going on. Or I don't. And I mean, yeah, it might be interesting, but I also don't know if it's worth the effort to look at making this type into a more abstract interface that you can explore, replace components, and so on. It's like a more general version of computing.
I just want to briefly add that if we think about kind of the constraints, rental constraint we were talking about before, this could fit within that. I mean, if you just put the runtime constraint to the decode time of some existing codec, then this is then a valid submission to that track, and so then so I agree it's interesting. One way to realize it or incentivize it would be to make the lowest track of the runtime constraints to be something that's only like 2 times faster than an existing code.
Maybe 2 other scenarios that we could handle. One is more realistic image or video calling. So if all the test images and video images were high quality, like you don't get that really in the real world. And that may cause a lot of these codecs not work well in practical settings. So and another one would be more of a constrained scenario, so like the talking head video that we saw and on one of the talks. That's a scenario that we maybe would do way better, either using text or avatars or something, to get a 10x improvement. And that's a very big use case.
Yeah, that makes sense. And obviously, I don't want to make your life more difficult, but also things like packet loss or even the streaming use case, just move the vframes. That would be a use way. But of course, it spreads out suspiciously more. It's now you have to handle 3 tracks. It does make sense.
To be fair, there's a suggestion. I mean, I looked at some of the submissions for the image tag, and the top contenders look pretty amazingly good, to be fair. So, like, I would consider it usable, which I never would have thought I would say of anything that compresses of 0.3 bits per pixel, even just 6 months ago. But there might be, especially if we want but maybe no, I don't know. There might be some sense in going a bit higher than like adding a 0.5 bits per pixel pack or something like that, for very high quality compression. Like basically, one question we could try to ask is, what's the bit rate? Like, what's the bit rate at which no one will be able to tell the difference under some test conditions? Whichever those may be. It's hard to say. Probably not a physical test.
Maybe that's something you can do. I personally move the other way. Especially for video, I think it's very interesting to ask how low can you go that people still don't notice. Especially if you have videos where there's a lot of movement. I would say it's unclear whether we are in a good achieve or not.
So I think one domain that we haven't talked about at all is 3D video. So if I could just snap my fingers and have another track that doesn't make a lot of extra work for me, it would be compressing point clouds or looking at other 3D content and trying to push the envelopes on that work. That's not just directly related to standardization, for example.
I just want to add that we could also consider the opposite, to just focus on one thing. I mean, I don't know what people think here, but it would, for me personally, also be interesting to say just focus on video. I don't know.
Yeah, I just want to say that it would be interesting to hear for participants or people who considered participating but didn't, how they feel about the number of tracks, etc. And the other thing is, please email us with your feedback and suggestions if you can come up with something right now. And yeah.
Right, so just I guess we've seen how the learns or AI-based image compression is outperforming traditional compression yet. In video tracks, we saw that the top 3 these participants will all still have PDC as a main component of this, and it's a it's a bit of a discrepancy that I'm having trouble to reconcile. So I wanted to hear your take on it. Do you see like how far do you see a place for purely AI-based video compression that can outperform the traditional compression?
In 4 years. No, I don't know. But I mean, clearly the difference is that there has been so much research. Even, I mean, I thought that was a nice slide from the Parka to see how it's still very much active. There's AOM, there's the MPEG group. So clearly it's much more challenging, and in my opinion, we also don't really know where we are with respect to these codecs. Auke brought it up with respect to RGB versus YUV and so on. I feel like in general, we have been maybe a bit sloppy comparing to these classical codecs. We don't. I personally don't know where we are. If we would, I guess I don't know what the settings they optimized really, but it would be very interesting to look at exactly that setting and compare there. As a starting point to know where we are.
I certainly agree with that. It's a really good question, although it's always difficult to predict the future, of course. I think one nuance that Laura also added and that I want to emphasize. We talked about niche topics, and Nick and I were talking earlier about what constitutes a niche topic, right? For Laura, it may be different than for me, but I consider YouTube a niche application of video coding. But when you think about what kind of impact it has, it's definitely a video codec with neural-based views, right? It's a big adoption. And of course, it's up to these guys to control whether it actually happens. So my answer to that question would be, we're definitely not there yet when you look at YG40, VSNR, and replacing standard codecs across the board. But niche use cases, which may be larger than you realize, are probably the closer.
I think we're about at time anyway. Yes, we're about at time. Thank you, everybody, for joining the panel discussion. We're going to move on to the award ceremony next, and then we will go down to the poster session. Slide for it. We also had a question about whether the recorded video will be open access. I think it's only going to be on the CVPR website for a week, but we are going to host that and as many of the presentations as we're allowed to on our website, compression.cc. So it should be there probably in the next couple weeks. This is incredibly hard to do on one window. Okay, so we're almost at the end here. We're at the award ceremony. The prize structure this year is we gave the top three in each of the leaderboard the same allotted prize. We also ask that people sort of self-report if they are an academic institution or if they're a company. We want to try to give this prize money to as many students and academic institutions as we can. We also this year are doing for the first time a Best Student Paper Award. This is a paper that was presented for the paper only track, and it has to be first authored by a student. So how this normally goes is I think I'm in contact with almost everybody, but I will contact you again at the end, and Radu from ETH Zurich will work with dispensing your prizes. This year, the money was graciously sponsored by Google, who also pays my paycheck, and InterDigital. So thank you, Google and InterDigital. For the perceptual metric track, we had 2 of the top 3 present today. IMCL T1 gets a $600 prize. IQALY got 2nd place, but is prize ineligible. And Kingslayer got 3rd place and also gets $600. So a quick round of applause for everybody. On the image compression track, Newbie Codec is number 1 and unfortunately prize ineligible. PKUSZ 201 is 2nd place, and IMCL T2 was 3rd place with $600 apiece. Congratulations. And finally, for the video compression track, the 1st place was Neutron Star, prize ineligible. ZXCRD 2022 in 2nd place, and YAVC in 3rd place. So thank you to these teams. And for our Best Student Paper Award, we want to encourage more student participation. Again, student has to be the first author. And we know the challenge tracks are very important, but they're also very competitive. And we want to encourage more student submissions. So we're giving our best student paper award to Anna Volokitten at, I believe it was ETH, who worked on neural face video compression using multiple views. So congratulations, Anna. And that's almost it for CLIC. We're going to have a poster session that got moved from Hall B and C to Hall D and E. If you have a poster, just go ahead and put it up at the first number you see between 225A and 253A. And I'll just keep this up for a second. And thanks to everybody for attending. Looking forward to the 6th CLIC in 2023.
So what do you think of this idea of the continuous test server?